That's my bad. Okay. Okay, then that's fine. Maybe we can start from there. Yeah. Okay, so what I was discussing is that so as we know that today's architecture is heavily motivated by data, but then uh, the architectures that we are looking at today, they are kind of going against the trend, right? So they are terrible at exploiting vast amount of data as well as metadata available to them to make autonomous and adaptive decisions. To some extent, we can say that these architectures are more of a human-driven as opposed to being data-driven. And at the same time, they're also terrible at, wait, something is happening. Okay, I lost this one. Maybe, I don't know why. What's going on? Okay, yeah. So, but at the same time, these architectures are very terrible at understanding and exploiting various semantics and characteristics of application data. So I'm going to talk more about this today. Yeah. Mm-hmm. No, that's fine. So I guess the video is not coming up. Is that the case? Yes, sometimes it doesn't come up. The spotlight needs to be removed and reapplied, and then it comes up. It happened last week also. It should be fine. Yeah. Let's just wait for some time. This is what human-driven infrastructure is. It's for, but we can be better. It should be fine. I think it should be fine. Thanks, Nisa. Come on, man. Yeah. Okay. So with that said, so the goal of my research is to design and develop architectures that are that kind of have broader two classes of let's say characteristics, right? So they can learn from vast amount of system data to make autonomous data driven decisions, as well as they can exploit data characteristics as well and the semantics to make data aware decisions. So you have seen, so these are the some key contributions of the research that we are leading with here. You have seen it in some prior lectures in prefetching. Hermes, you have also got introduced a bit on the prefetching lectures. And so what we are going to discuss today is the Constable, which kind of presented this year itself. So that's an application of the data aware microarchitectures, and then we are going to discuss what exactly that means. So that's the name of the work, Constable, improving performance and power efficiency by safely eliminating load instruction execution. So the key problem that this work tackles is that, you know, we know that the load instructions are the key limiters of instruction level parallelism, which is fundamental to extract in performance from today's high performance systems, right? But then these load instructions, they have two sorts of dependence which limits this ILP. One is data dependence, meaning that a load instruction stalling other load instructions due to a load stalling other instructions due to the long load execution latency. So any data dependent instructions on this load cannot be executed before the load executes, right? And then we have the resource dependence, which means that the load instruction is stalling other load instructions due to contention in pipeline resources. Like, for example, you can think of like address generation units, whatever is what's going to be the address of this load instruction. So there is some hardware unit that generates the address. Then you have load ports, which actually executes the load and then accesses the memory, the cache structures, and so on and so forth, right? So all of these resources are heavily contented across the load instructions. So that creates this resource dependence, right? Now, we have a lot of works stemming from early 1990s, right, that tries to tolerate long load execution latency. So these are the two broader category of these works, load value prediction and memory renaming. So they are fundamentally mitigating the load data dependence by speculatively executing the load instruction using a predicted load value. So that means you can now execute the data dependent instructions without stalling for the load. Once the load completes, then you can verify whether your prediction was correct or not, right? But then they do not mitigate the resource dependence, because these predicted loads, they still need to be executed to verify the speculation, thus consuming the hardware resources that they were consuming in the baseline anyway, right? So the goal of this work was that, okay, can we safely break the load data dependency without even executing a load? In that way, we can actually provide additional performance benefit what these other techniques like load value prediction and memory renaming couldn't provide. Okay, so that's the whole motivation for this work. Okay, so with that said, so this is the executive summary of this work. So we kind of make three key findings. First, we saw that in general purpose workloads that we normally execute in CPUs like very aggressively. So these general purpose workloads, a significant fraction of the load instructions, they always go to the same address and they always fetch the same data. We are going to discuss why that's the case and going to see some examples. We show in this paper that a significant fraction of these loads, they cause resource dependence. And if you eliminate this resource dependence, there is a significant amount of performance headroom to be had. So that's the three key findings of this work. And with that said, we are going to propose Constable, which is the key idea of Constable is to mitigate both load resource dependence and data dependence by safely eliminating the entire execution of a load instruction. And we're going to show that it's going to provide performance as well as power benefits, because you're not fundamentally executing an instruction on top of a strong baseline out of order processor that already has lots of optimization going on. Okay, so that's going to be the the brief overview of today's talk. So let's start with the key findings. So as I said, like we started by analyzing load instructions present in general purpose out of order execution codes, and we saw that there are some loads that repeatedly fetch the same data from the same load address throughout the entire workload that we are looking at. Okay, so what does this mean? This means that both the operations of these load instructions, the address generation and the fetching the data from the memory, is repeatedly doing the same work again and again. Okay, so which means that these are the prime targets. If you can simply you can eliminate these instructions without even executing them. Right? So you can eliminate their data dependency, and we are also going to show that the moment that you are not executing, it's going to eliminate the resource dependence also. So for the sake of the easiness of the presentation, we are going to call these loads as global stable. Global meaning it's stable across the entire workload that we are looking at, and stable meaning that they are generating the same address and fetching the same data. Okay, so this is what the fraction of the loads on the y-axis. You are seeing the fraction of the dynamic loads. X-axis you are seeing different workloads. And what we are seeing here is that nearly 1 in every 3 load instructions that we are seeing in general purpose workloads are global stable. So the meaning that they are always going to the same data, same address and fetching the same data value from them. Now, before going, you might be asking that, okay, hold on a sec. Maybe you are not looking at the most optimized code, right? So that's why these load instructions are there. That's a genuine question. You might be also looking at, okay, what type of architecture that you are simulating? Is it x86? Because x86 has less number of registers. So that might be evident from you that, okay, maybe these loads exist because you have less number of registers. If you have more number of registers, then loads vanish, right? So that's second question. And then you might be asking all sorts of questions like why these loads are there? Like, are they accessing constant values? Are they inside some sort of small loops that getting executed again and again? So I'm going to answer some of the questions in today's lecture, and I'm going to defer to the paper for the remaining questions. Okay, so let's start with the first one. So are we even looking at these load instructions in the most optimized code? So to answer that, let's see one example of what's happening, right? So this is one example from this workload, the Leela from Spec CPU suite. So this is what the code looks like. So this is a random variable, right? So that's a global variable. We all write code like this. So that's a global singleton variable. And then we have a get RNG function, which says that, oh, if the variable is not initialized, then initialize the variable. Otherwise, simply just return the variable, right? So this is how the code looks like. And then this is well optimized with GCC, fairly decent GCC with minus O3. That means full optimization enabled. And this is how the code gets laid out, right? So this seemingly harmless, the if clause, right? So SRNG equals 0. It's actually getting converted to a load instruction. It's saying that, oh, this is the instruction pointer. And based on that instruction pointer, let's fetch the value, this offset away from the instruction pointer, get it to the RAX register, and then test the RAX register with itself. So that means it's 0 or not, right? If it is 0, then do something, otherwise do nothing. But then the question is that we know the way that we are writing the code, we are initializing this srng variable only once, right? In the very beginning of the code somewhere, right? So that means by the virtue of the way we are writing the code, this load instruction gets initialized only once, and that's a global stable load. And what happens is that means this load instruction also becomes a global stable, meaning that they are always going to the same address, fetching the same data, never gets changed, right? Now you might be thinking, okay, can the compiler not optimize this instruction? Let's say have a register that is allocated for this load instruction instead of reading it from the memory. It's possible, but then you also need to allocate that register throughout the entirety of the program, because this is a global scope variable, right? So that means that register would stay live throughout the scope of the program, which GCC and any sane compiler would say that, okay, I'm not going to allocate a register for that. And hence you ended up having a global stable load instruction. So there are other examples also. This is in the paper. I'm not going to go too much into detail, but this is one example. This one is another example that we have. Okay, for some reason this is completely blown out, but we have even though we write a code like a function that takes, let's say, variable size argument, right? The out size as a variable. The way we call these functions, we call the same the functions with the same arguments again and again. So that also generates this sort of artifacts that, okay, you are seeing a load which is going to always the same address and getting the same data because you are passing the same arguments to this function again and again. Okay, so in a nutshell, what we saw that these loads can exist for many reasons, right? So they can be accessing global scope variables, right? By the way, if you have worked on, let's say, any simulator environment, like be it processor simulator or the world simulator inside games, right? So these global variables would be very much apparent if you're into the game development. So there are lots of global variables out there. And then we can be having, let's say, local variables of an inline function. We can be this can be coming up from the fact that there are limited architectural registers, and there can be multiple other examples also for why this load can exist. Okay, so with that said, so that means we are kind of answering the first question. Second two questions, I'm not going to go too much into detail for the brevity of time, but you can always go back to the paper if you're interested. Okay, so what we saw is that the significant fraction of loads are global stable. Then the question naturally arises that, okay, do they limit ILP due to resource dependence on top of a system that already has both of these predictions going on, right? So load value prediction, memory renaming, which is very good for alleviating the load data dependence, right? So to answer that, we kind of went inside and then looked into what's happening with the code execution. So what we are seeing here is the total number of execution cycles, a fraction of the total execution cycle on the y-axis. X-axis is the workloads, and what we are seeing here is that the number of cycles, at least one load port is utilized. So that means you have an execution port for the load instruction, and for that cycle, at least one of them is utilized. Why at least one of them? Because this is coming from a very aggressive out-of-order processor that has 3 of such load ports. Okay, so at every cycle you can execute 3 instructions. Processor is designed for that, and this processor also has a load value predictor and memory renaming enable. So think of it as a very beefed up state-of-the-art processor design, right? So let's see what happens in that case. Okay, so what we are seeing here is that almost 1 out of every 3 cycles, at least one instruction is causing load port consumption, right? So now if we break down that 32.7% fraction, let's say, okay, who is accessing the instruction load port, right? And then if we try to break it down, so again on the x-axis we are going to see the workloads, y-axis we are going to see the load utilized cycles, meaning all of these, right? So that's going to be the 100% in this graph. So what we saw is that 23% of the fraction of these 32%, right? So that's the combined fraction. So those many cycles, we are seeing that it was a global stable load that took the load port, while there is a non-global stable load waiting on that port. So it's like 2 of them are fighting for the same port, and one of them won, and that's what we are kind of having this situation, right? So it's somebody went on and just utilized the port. So somebody who needs that port for its genuine execution cannot get it. Now there is 22.8% or more where a global stable load is utilizing the port, but somebody is not waiting. So there's still somewhat, let's say, yeah, optimization targets, but then at least they are not as bad as this 23%. Okay. And then the rest is, the most of it, which is saying that, okay, the port is actually utilized by a non-global stable load, meaning that they are getting used for doing some meaningful work, and life is good, right? So what we are seeing here is that these two classes is problematic, right? Because somebody is utilizing the port, which should be, should not be that, let's say, hard to predict. But then, the good or the needy loads are still waiting on that same port. Okay, so that's what the source of the inefficiency comes from. So what we are then, what the takeaway from this figure is that what we saw is that even though we have all of these techniques like load value prediction, memory renaming going on, still they can have load resource dependence stemming from these loads, right? Then the question is that, okay, do they have performance benefit if we kind of eliminate these global stable loads, right? So that's what we try to answer here. So again, on the x-axis you have all the workloads, y-axis you have the geomin speed up over the baseline. Baseline meaning the system that already has all of those mechanisms going on. So what we are seeing here is that if we completely eliminate, ideally meaning we know what the load is supposed to do, right? What's the address is going to go, what's the data is going to fetch, and we just simply say that, okay, that load is magically executed without taking any resources whatsoever, right? So that means it's eliminating both the data dependence, meaning that if it instantaneously executed, that means any dependent instructions, the data dependent on them, can be executed also without waiting for any cycles. And at the same time, they are also not causing resource dependence because this is magically executed. We are not taking any resources either. Okay. So what we are seeing is that if you do that ideal elimination, that provides a decent 9.1% performance headroom. And then if you do the same thing only for the value prediction, meaning that you're just simply breaking the data dependence, the load still executes. It takes all the resources, whatever they want. So that only gives us 4.3%. So that basically shows that there is a significant jump if you remove the resource dependent also. So that's the benefit that we are chasing. Now, you might be asking that, okay, isn't 9.1 too less of a headroom, right? So that's quite a genuine question. So what we are, but you also need to put it into a perspective that this is, very strong out of order processor that has been optimized over generations, probably across for 50 generations. So to put it into a better perspective, if I just simply, let's say, double the number of load execution ports in this processor, right, whatever the baseline is, that actually gives 8.8% performance headroom. So that means what you're seeing here is that the headroom that you're looking at by ideal elimination is literally mimicking a processor that has twice execution capability of loads. And by the way, this configuration is really hard to achieve. Not hard to achieve. This configuration is, let's say, power intensive because you need more ports. That means you need lots of ports to the data cache, which adds the power, as well as it's also area intensive because the more number of load ports that you are going to have, the more the size of the chip goes, right? So what we're trying to say is that it's kind of matching the same benefit or even going better than that without having any of these area or power overhead, or let's say minimal area or power overhead. That's a benefit here. Okay, so with that said, so now I would just simply go one bit historical perspective here. So that's what we are meaning by why the load execution port doesn't grow, right? So this is one chart that shows almost 15 years of development of Intel processors. I'm not sure why am I nitpicking on Intel, but the trend is almost similar here, right? So the load execution port, as you can see, it has grown, let's say 50%, right? But if you look into the other resources that has grown in the processor, right? Like for example, reorder buffer size and total number of execution port also, like how many ALU instructions you can execute, how many logical instructions you can also execute. So that also increased quite a significant amount as compared to load. Why? Because they are fundamentally limited by area overhead, power overhead, and so on and so forth. So that's the reason why we are not seeing this sort of artifacts more in today's processor. So with that said, we believe that this sort of load resource dependence is going to be even critical in going future generation processes. They are problematic in recent generation. Going forward, it's going to be even more problematic, and that's what we are going to solve in this case. Okay, so that's the goal of this work, that to improve the instruction level parallelism by mitigating both the data as well as resource dependence, and that's what Constable is. So Constable is kind of a purely microarchitectural technique that does both of these by safely eliminating entire execution of a loaded instruction. So let me give you some idea, the broader overview of how Constable works. Okay, so think of this as the dynamic instruction stream, right? So your program is executed in this way. So these are the instructions that you're looking at, right? So these are the two highlighted load instructions, right? So let's call it so and another thing is that these two are the same two dynamic instance of the same static load instruction. So think of it in this way, that this instruction is inside a loop, let's say, and then you are executing that loop multiple times, right? So this is one iteration of the loop when you saw that instruction. This is the other iteration when you saw the other instruction. Okay, so they are the two dynamic instances, successive, of the same static load instruction. Static meaning they are in the compiled code. Dynamic instance meaning they are the two dynamic versions of it. Okay, so let's call them LD1 and LD2. So what we can say that if the source register of this instruction, which is the RBP in this case, the register stack base pointer, right? So if the source register has not been modified between these two occurrences, for guaranteed that LD2 is going to have the same address as LD1. Okay, so there is a theoretical guarantee. So that means that the address generation of LD2 can be eliminated without even doing that address generation, right? Similarly, if you know that, okay, no store or the snoop request has gone to the address of the previous instruction, right? So store meaning my own code is not modifying that memory location, and snoop meaning some other code. I guess you have already seen it from the coherence lecture, right? So snoop meaning from some other code is also not accessing that same location, right? So if no store or snoop has gone to this address, that means you know for sure that LD2 is going to see the same data as LD1 also. So that means LD2 data fetching operation can also be eliminated, right? So that's the two key insights that Constable builds upon. It says that, okay, fine, then how it's going to work? It works in two steps. First, it dynamically identifies load instructions that have history of fetching the same data from the same address. So it's basically in the beginning, it says that, okay, I'm not going to do anything. I'm just going to observe what's exactly happening, right? So what are which load instructions are fetching the same data repeatedly from the same address? And once you know that these are the instructions, then you target their execution, say that, okay, for these instructions, you are going to track the modifications of their source register as well as modifications on their load address to start this elimination process. Okay, so how the elimination process works, let's see a bit overview. So for the identification process, it's a simple stability confidence mechanism. So whenever you see, let's say the current instance is fetching the same address from the same, fetching the same data from the same address as the previous instance, you're simply going to increment the counter. Okay, whenever you see that, oh no, the value is either different or the address is different, right, then you are going to halve the counter. So that's a like a arithmetic increase, geometric decrease sort of confidence mechanism. Once you reach a certain confidence threshold, saying that, oh, this is now, I have enough confidence on this load instruction, saying that this is probably a target for me, I can probably eliminate their execution. So at that point, when the stability confidence threshold is reached, what you're going to do, you're going to say that, okay, there is a register monitor table which says that, okay, I'm now going to track this register, which is the source register of this instruction. And I'm also going to track the address of this instruction, which is let's say the executed address. You're executing this guy, but not the subsequent one. So that's the address that you know, and you're going to track this. And at the same time, you're also going to say that, oh, this load instruction is now eliminatable, which is the eliminate flag, which you said that, okay, now you can eliminate. So what that flag essentially means, the moment you would see the next iteration of the next instance of this instruction, you're going to simply look up this table saying that, oh, the flag is set. Yes. So that means you can probably eliminate this instruction. Eliminating means you're not going to take any scheduler entry, which is the reservation station in Intel's terminology. You're not going to take any address generation unit. You're not going to take any load port for this instruction. So that instruction, as if kind of magically executed. And what's the value of this instruction? You're going to get it from this table itself. So you can use this value to unlock the dependence of this load. So now the dependence can also go on. It's as if that you have magically executed this, right? At the same time, it also takes some sort of other resources, which is not getting eliminated. It's a good idea to think of how to eliminate these resources also, because they are also very critical for performance, right? But as of now, we have made up a decision that, okay, we are not going to eliminate these resources for now, because there are multiple, considerations for this. Okay, so as long as this flag stays on, any subsequent instances of this instruction would get eliminated, right? So using the same value. So the flag essentially means that nobody has touched your register, neither no store or snoop request has gone to this address. So that means any subsequent instance is bound to see the same data, and it's also bound to go to the same address. So you have a guarantee, you start eliminating. Yeah. For this. Okay. So let's So let's see. Now you have an instruction that changes the RBP, right? So that's a genuine question, right? So what if the RBP changes, right? So a register cannot get modified unless it's explicitly used as a destination, right? So you know that, okay, there is an instruction that has this source register as a destination. The moment you would see that, okay, this register is getting modified, you would look up into this monitor table and you would say that, okay, who is supposed to use that register as its source? It's PCX, fine. So let's go to the elimination table and then say, now I cannot eliminate this guy forever from now on. So the moment you would reset this flag, it essentially says that, okay, any subsequent instance, even though your confidence might be high, right? But just because the flag is now not set, you would say that, okay, now I need to execute this flag. Why? Because there has been some modifications that has been done on the source register. Even though that might be very well that this modification does not modify the value of the register. It can very well be the case that you have same register value and then you modify it with also the same register value. That happens. And that happens quite a lot in the, we have mentioned in the paper. But still in this mechanism, you don't have any other option not to stop elimination for this instruction. Okay. So with that said, so there are lots of more, mechanism details in the paper, like how exactly we are going to, ensure safe elimination in the out-of-order processor, multi-threaded, multi-core executions. I'm not going to go into much detail. I'm already, I guess, running out of time. So I'll go through some brief of the methodology. So we evaluated this idea in a industry-grade x86 simulator with a very wide out-of-order process, wide out-of-order fetch with memory renaming, load value prediction, all sorts of elimination strategies like zero elimination, constant elimination already implemented, and we have kind of analyzed with lots of different sets of workloads, right? Not only just the spec, but also lots of client workloads like what we use in today's laptop systems, or maybe as a desktop consumers, enterprise workloads, server workloads, and so on and so forth. And there are lots of mechanisms that we have compared against, both in simultaneous multi-threading and two-way SMT systems, because in SMT, the same resources gets even congested by the other thread, right? So the resource contention is even more severe in SMT systems. So that's the target for us to even evaluate. So what we saw is that if you so EVES is the state-of-the-art load value predictor. So as you can see that if you have Constable by itself, it outperforms EVES because now it eliminates both the the data as well as resource dependence. But now if you add two of these together, then that provides additional performance benefit. Now if you look the same, now if you look into the same graph for the two-way SMT system where the contention is even more severe, the performance benefit is even more higher, right? So Constable by itself provides decent performance benefit, but then if you add both of these together, that provides additional performance benefit on by each individual mechanisms. Okay, now just because you are also eliminating instructions execution, not doing it all together, so that also improves the resource efficiency. Resource efficiency meaning if you look into the L1 data cache access, that gets reduced, right? So that's the the reduction bar that we are looking at. So on average, we are seeing 26% of the data cache access also getting reduced. The same way that the reservation station, meaning the scheduler in the out of order processor, that's also not going to be taken by this eliminated load. So that also gives us a 8.8% reduction in the scheduler entries, right? So that's not the number of entries that are not getting used. And this directly gets transferred into, the energy savings, right? So what we are seeing is the reduction in the dynamic power. As you can see here, that the L1 data cache reduction, dynamic power gets reduced by 9.1%. Similarly, the reservation station, which is the prime factor of the out of order unit power, that also gets reduced by 5.1%. So that's the benefits here, and that's the overhead. Obviously, it's not that high, but for sure this is a complex mechanism. So if you want to implement in the processor, that might have questions about the verifications and stuff. But we believe that this is very significantly lower overhead for sure compared against just doubling the number of load ports. Okay, so with that said, so that's the summary of this work. So as I said, that there are three key findings. A large fraction of the load instructions are global stable, meaning they're fetching the same address and the same data. These global stable loads cause resource dependence, as I show. And if you eliminate them, rather than just simply breaking their data dependence, they have performance benefit fundamentally than what just breaking the data dependence would provide. So that's Constable. We show that, okay, Constable provides high performance benefit. It improves resource efficiency, reduces dynamic power while giving it for the low overhead. Now, with that said, as I said, if you're interested, read the paper. There are lots of headroom that are still left. Like what we identify offline, only 57% of that targets are like the targets of global stable loads are actually getting eliminated online. Okay, so there are lots of headroom that are still left, which if you're interested, like why they are not getting eliminated, what's the software construct, there are tools available online also, which you can just simply run it with your own, like the programs that you are running in software, any software that's out there in running in Intel system. You can actually identify like how many of these loads are there in any out of the shelf software. And if you're interested, just play around with the tool. Okay, so with that said, I'll hand it over to Konstantinos. And while this change is happening, if you have any question, I'll be happy to take. Okay, we have any question? If not, then Konstantinos, this is your stage.
Can you hear me well? Can you hear me? We can start whenever. Shall I begin? Okay. So I'm Konstantinos. I'm going to deliver the second part of the lecture. It's going to be around the topic of virtual memory, which is what I'm working on nowadays. Who am I? I am a PhD student at the Safari Research Group, working under the supervision of Professor Onur Mutlu. I finished my undergraduate studies at the University of Athens, the National Technical University of Athens, and I'm interested in hardware, software, co-design research with a focus on efficient memory management. And I contributed to other works related to security and microarchitecture, like what Rahul has been working on. You can find more about me on the website. So in today's talk, we're gonna talk about two papers which were presented last year in Micro 2023. One of them is about how we can use the existing cache resources to make address translation much faster. And the second one is how we can rethink the abstraction of virtual memory so that we change the address, the virtual address to physical address mapping and accelerate the process. After these two works, I'm going to discuss about the simulation framework which I've been working on with Konstantinos, who is sitting over there. Then I will jump into some challenges in the topic and some potential research directions that we could work together on. So the first work is Utopia, fast and efficient address translation via hybrid, restrictive, and flexible virtual to physical address mappings. Let's dive into the executive summary first. So we have the conventional virtual to physical address mapping, which is very flexible. What does that mean? We can place any virtual page to any potential free physical page in the memory. However, this leads to very large translation structures, which means the page table. What does this lead to? High translation latency and large translation-induced interference in the memory hierarchy. We have data and metadata for the translation competing with each other in the memory hierarchy. And what's the motivation behind this work? If we could restrict the virtual to physical address mapping and we don't place its page in any potentially free physical page, then we could fundamentally reduce the size of the translation structures. But if we do this across the entire physical memory, it has two major drawbacks. First, it limits the core virtual memory functionalities such as data sharing. We cannot guarantee that we can place two different virtual pages on the same to point to the same physical page. And second, it might increase the swapping activity in the presence of free physical memory. If we cannot map our desired virtual page to a free physical page because the hash function does not match, then we need to place it in the swap space, which would increase a lot the overhead. What's our key idea? Key idea is Utopia. It's a new hybrid virtual to physical address mapping scheme that allows both flexible and restrictive hash-based address mappings to harmoniously coexist in the system. So Utopia manages physical memory using two types of physical memory segments. On the left, you can see a page, a virtual page, which we want to map to the restrictive segment. So in the restrictive segment, we can map this page using a hash function. So this page can only map to a specific part of the restrictive segment. For example, here we use the modular hash to map it in the restrictive segment. What does this offer? Very fast translation, because we simply need to calculate the hash result. However, it limits, as I said before, the virtual memory features. And on the other hand, we have a page and a virtual page that we want to map to a flexible segment. And in this scenario, we can map it anywhere we want. How do we do this? Using a dictionary, which is a page table, basically. In this scenario, we assume that the page table is like an x86-64 radix tree. And what's the problem with this? It leads to very slow translations also later. But on the other hand, it supports all the existing virtual memory features. So it doesn't have swapping problems. It doesn't have data sharing problems. Our key results in this work is that it outperforms the state-of-the-art contiguity-aware translation scheme by 13%. This is the second best performing and state-of-the-art scheme, and achieves 95% of the performance of an ideal perfect TLB, where we simply hit in the L1 TLB as an Oracle study. The code is online and you can find it on GitHub. This is the outline of my talk. I'm going to deliver a bit more background in the first paper, and then we're going to reuse the same background in the next papers. So virtual memory is one of the cornerstones of most modern computing systems. Conventional virtual memory designs provide three things, basically. Application transparent memory management. So the user who writes their programs do not need to use physical addresses directly. They can use virtual ones. Second, data sharing. We have multiple users which might want to share the same library, for example. They can share their data through virtual memory. And third, process isolation. The users do not need to care whether they will overwrite the data of another user. And a core feature of the virtual memory management is that the mapping between the virtual and the physical pages is fully associative. What does that mean? This means that whenever I want to map something from the virtual address space to the physical address space, I can place my page wherever I want. And how does that happen? If I store the information in a dictionary like the page table, that's very straightforward. So how do I find, though, the mapping between the virtual address space and the physical address space? Through a process which we call a page table walk. And the page table walk allows us to retrieve the mapping using the virtual address. How does the page table walk look in x86-64 systems? So we have a virtual address here, and let's say we split it into four 9-bit segments. We use the first 9 bits, and we access the root of the tree. Using the content of the corresponding entry, we access the next level. And we do this recursively until we reach, iteratively and recursively, until we reach the last level. When we reach the last level, the content of the last level, it's the physical frame number. So after we retrieve the physical frame number, to retrieve the physical frame number, we need to do 4 memory accesses to each one of the levels of the table. So we have 4 sequential memory accesses during a page table walk, which I will show later lead to high performance overheads. So if we want to send a request to the memory hierarchy, to the cache hierarchy nowadays, the processor needs to translate the virtual address to the corresponding physical one. And if every time I want to translate, I need to perform 4 memory accesses, then I will tank performance, basically. So to avoid this issue, modern processors employ a specialized unit called the memory management unit to accelerate address translation. So this is the address translation flow right now in the core microarchitecture. The core sends ships the virtual address to the memory management unit. So the memory management unit is a pure microarchitecture unit that handles address translation. What does it do essentially? It communicates with the memory hierarchy about the contents of the page table. There is a 2-level translation look-aside buffer hierarchy. So translation look-aside buffer is a small cache that stores the most recently page table entries. Then there is a 2-level hierarchy of these. When we ship the virtual address through the TLBs, we probe them and we ask the question, is the page table entry that corresponds to the physical page available in the TLBs? If yes, we do not need to go and read the page table from the memory. We find it in the TLBs. However, if we miss in the 2-level TLB hierarchy, we need to trigger a page table walk process. There is a circuitry in the modern processors called the page table walker. Imagine it as an FSM that goes and accesses the page table from the memory hierarchy. It generates requests and asks for the page table entries from the memory hierarchy. But if we would ask for every request, again, upon a miss, we would perform 4 requests, right? But the page table walks are using the page table walker is using page table walk caches, which store the intermediate PT entries. So you can store translations from the second entry of the page table, from the second level of the page table to the third level of the page table, not directly from the first level to the 4th level. And this helps us skip some steps during the page table walk process. But if we miss in this cache, then of course we need to load the page table from the memory hierarchy, which means we might load it from the L2 cache, from the LLC, from the main memory. Let's see the straightforward scenario. We fetched our page table entry. We found out the physical page number, and the data is in the memory. So we send the physical address to the cache hierarchy, and we're waiting back for the data. That's pretty straightforward. The most cumbersome scenario is when a page table entry does not reside. It says that the data does not reside in the memory hierarchy, and it resides in the swap space. So imagine the swap space as part of the disk, which we're using to oversubscribe DRAM, basically. So if we find that this happened, then we trigger a page fault because we need somehow the OS to handle this sort of access, because I cannot access directly the swap space. So the OS handles this sort of access. It swaps in the memory corresponding page, and only then I can generate the physical address and go and fetch the data from the cache hierarchy. So this is the translation flow. And let's talk about the translation latency a bit. So what's the good scenario? The good scenario is that we hit in the TLBs. We find the page table entries inside the TLBs, which means we find the corresponding physical frame number in the matter of tens of cycles, maximum. The worst case scenario is that we missed in the TLBs, and we need to somehow fetch and retrieve the page table from the cache hierarchy. And in this scenario, you might basically wait for a cache access or a DRAM access, which might lead from 20 cycles, 30 cycles, up to 200 and 300 cycles, as I will show later. Let's talk about the address translation overheads right now after we covered this whole background. We have many data-intensive workloads, generative AI, graph analytics, bioinformatics workloads, which cause very high address translation overheads. The process that I showed before costs a lot in these workloads. we have high latency page table walks and very frequent page table walks, which is a result of the irregular memory access patterns that we see in these workloads. In this plot, I demonstrate the page table walk latency across two configurations, the radix-based configuration and a state-of-the-art page table which is used in the literature. And we demonstrate that even with a state-of-the-art hash-based page table, it's not a conventional radix tree, this leads to 86 cycles on average to access it, which means that if I'm missing the L2TLB, I need to wait for 86 cycles to retrieve my translation. And someone could say, if the page table walk is not frequent, then it doesn't matter. But in this plot, we demonstrate in the y-axis the L2 TLB misses per kilo instructions, how frequently we're missing in the L2 TLB across different L2 TLB sizes, ranging from 1.5K entries up to an extreme scenario where I have 64K entries in the L2 TLB. And we demonstrate that even if I make my L2 TLB extremely large with 64 kilo entries, then I still experience 24 misses per kilo instructions, which means that every 1,000 instructions, I need to perform 24 page table walks. And this causes high performance overhead still, even if we go for very large TLBs. So we have high latency page table walks, frequent page table walks, which together lead to high performance overheads and high interference in the memory hierarchy. In this plot, we make an idealized study. We take as a baseline the radix-based system, and we use the state-of-the-art page table, which is proposed in the literature in a paper from ASPLOS 2020, and a perfect TLB scenario. The perfect TLB means we always hit. And we do this experiment so that we can see the headroom, how we can aim in terms of performance, whether we can optimize this problem. And as we observe, if we completely avoid translation, this leads on average to 31% higher performance compared to the baseline system, which gives us a 31% performance headroom to work with. And in this plot, we demonstrate, again, for the same configurations, the row buffer conflicts, which means how much interference do these translation requests cause in the memory hierarchy, in the DRAM. And we observe that if we completely avoid address translation, which means we have a perfect TLB, this leads to 30% fewer DRAM row buffer conflicts. And it could be very important, not just in single core scenarios where I simply run my workload, but I don't want to also destroy the locality of other workloads in the DRAM row buffer. So what is the idea behind this work? The idea is that, okay, we can restrict the virtual address to physical address mapping to perform very fast address translation. So we have a virtual address space and a physical address space, and we want to map, let's say, this page to the physical address space, to some physical page. So in this scenario, we do it through a hash function. Let's say we use this hash mask, and we map it only to a single physical page in this scenario. So what does this mean? That we can, using this hash function, we can simply take the virtual page number, hash it, we retrieve the physical page number. However, if we do this across the entire memory, as I said in the executive summary, it comes with two major drawbacks. First, it limits the core virtual memory functionality such as data sharing. And second, it increases the swapping activity, since the system cannot map pages to free physical pages. Going back to this figure, if, let's say, this page was the only one that you can put our data in, but it is not, it is already occupied, then what do I do? Where do I place my data? I need to place it somewhere else, for example, in the swap space. And this would cause high overheads. So here we did exactly this study. So in the y-axis, we show how many accesses you do to the swap space when you use only the restrictive mapping across the entire memory, compared to a scheme that uses a very flexible mapping. And we demonstrate that the sole use of the restrictive mapping leads to a 2.37x higher swapping activity compared to the baseline system. So the goal of this work is to design a virtual address to physical address scheme that provides fast and efficient allocation using a restrictive hash-based address mapping. But at the same time, it enjoys the benefits of the conventional fully flexible address mapping. So the key idea of Utopia is to use two mappings, the restrictive and the flexible mapping, so that they harmoniously coexist in the system. How do we do this? With two different physical segments. I mean, that's a natural choice. We have restrictive segments and flexible segments. The restrictive segments we take a virtual page number, we hash it, we retrieve the corresponding physical page, offers fast address translation, but at the cost of limited virtual memory functionalities. In the case of the flexible segments, our virtual page number, our virtual page can be mapped anywhere because we use a page table. In this scenario, we support all the existing conventional virtual memory features at the cost of higher address translation, high latency address translation. Let's see the properties right now of the restrictive segments. Two properties, the structural properties, how do we architect it? And second is, how do we actually do address translation for data inside the restrictive segment? So the restrictive segment is organized in a set associative manner, similar to hardware caches operate. What does that mean? This is an example of a two-way associative restrictive segment with two sets. So in this scenario, we have two sets. Each one of the entries is a 4 kilobyte page, and each set has two ways, way 0 and way 1. What does this offer? If we have a conflict, we are going to search through the sets where to place our data, so that we don't have a direct map behavior, or we simply, in a case of a conflict, we would put our data back in the swap space. And we can use multiple restrictive segments in the system. For example, right now, nowadays, systems are using both 4 kilobyte and 2 megabyte pages. So I could benefit by using one segment for my 4 kilobyte pages to deliver fast translation for 4 kilobyte pages, and another segment which is organized to store 2 megabyte pages, not 4 kilobyte pages. This sort of design offers backwards compatibility with large page mechanisms. Let's see right now how address translation is happening for data that reside in a restrictive segment. What is the problem? We have our virtual page, right? And we need to find out. So our virtual page is stored in this spot, in the first page of the restrictive segment. And the question is, how do I find out that this virtual page resides in set 0 and way 0? That's the question we need to answer. How do I find this out? Two operations, tag matching and self-filtering. Tag matching is the analogous to what happens right now in the hardware caches. So the tag matching requires comparing the tags of all the ways in my set with the tag of the virtual page that I want to access. And to enable this, we use a tag array that stores the tag of each one of the entries. We take the virtual address, we find out the set index and the tag. We go to the tag array and we find out, oh, nice. The first tag corresponds to my virtual page, which means that I can access this. So the first two elements here of the tag array correspond to the set 0. The next two elements correspond to the set 1. Someone can ask, okay, why do I need a tag matching? I could simply hash and go check that my data is in there. But this is not the case, because even two virtual addresses might correspond to the same set index, right? So I could not go and simply avoid the tag matching. There's no way that this can happen, because there's a case of hash collisions. Same principle as the case of hardware caches. And the question is, do we always need to do tag matching? What if a workload does not use this, right? And the answer to this is set filtering. So we want a way to quickly discover if a set in the restrictive segment is empty or not. And we want to filter the tag mismatches. So a set filter is basically an array of counters that keep track of the number of pages inside the set. And after the virtual page is retrieved, we calculate the hash function, we get the set number, and we access a bitmap basically that says, oh, data in the first set, there is some data in the first set. So you should do the tag matching if you think your data is in the first set. In this scenario, we cannot avoid the tag matching. However, if our data, if the set index was 1, then we would go here and we would abort the tag matching. We would not need to do tag matching because we know there's no data stored for me in that set. So that's the end-to-end flow of address translation in Utopia. We have two restrictive segments, one for 4 kilobyte and one for 2 megabyte pages, and one flexible segment. The rest of the memory is organized as a flexible segment, and we have two segments which are organized as restrictive segments. So on an L1 TLB miss, we need to do two operations in parallel. We need to do this restrictive segment walks, the process of finding out if a page is in the restrictive segment or not. We do one for the 4 kilobyte pages. We do one for the 2 megabyte pages because we do not know the page size a priori. But in parallel, we can perform the L2 TLB access. And if we find out that our data is not in the L2 TLB, and the data is not in a restrictive segment, then we fall back to the conventional mechanism where we do the page table walk using the x86 radix page table, for example. Some challenges. Which data should be placed in the restrictive segment? We said that, okay, the restrictive segment offers fast address translation, but which data should I place there? How do I choose this? Second, how can I maintain restrictive segments in the system so that they coexist with the flexible segment? Third, how can I integrate Utopia in the address translation pipeline? Yes. I will discuss this. Because I will show you the mechanism. It's a trade-off in general. So in terms of the page placement, our goal is to place the costly to translate pages inside the restrictive segment. And we propose two techniques to perform this. One is on a page fault, we will allocate everything in the restrictive segment as much as possible. And we need also a more dynamic mechanism that tracks on the fly which pages are costly to translate, which is the page table tracking-based policy. Let's see the first policy. So in the beginning, the OS attempts to allocate the page directly inside the restrictive segment. So on a page fault, if let's say we can allocate our segment due to the occupancy inside the restrictive segment, we go forward and we allocate it in there. If not, then we fall back into the restrictive segment because we cannot allocate it in the restrictive segment. Then we fall back to the flexible segment. And the question here is, if the restrictive segment gets full and you cannot directly allocate there, what happens with costly to translate pages which are coming simply later in the execution stage? So we use a page table tracking-based migration policy that uses some unused bits in the page table entry as a counter that tracks the number and the cost of page table walks. And we use here as a cost the number of accesses to DRAM that the page table walk triggered. This is a page table entry, and we use the unused bit as a counter. Whenever these counters exceed the threshold, then we migrate the page regardless of the occupancy inside the restrictive segment. Second, how can we maintain restrictive segments in the system? So we introduce OS support for Utopia in 3 ways: allocations inside the restrictive segment, replacements, because if we need to replace some data, we need to have a replacement policy. Someone needs to handle this, and this is the operating system. And third, migrations to and from the restrictive segment. How does allocation happen? We have the hash function, and we have the OS has a global view of the tag arrays. So the OS simply needs to keep track of the pages inside each one of the restrictive segments. If there is a free way in the restrictive segment, we store the data there. If there is no free way, then we need to evict the page, and the OS decides which page to evict using a replacement policy that I describe in the paper. How do we handle migrations? The DMA engine is basically responsible for migrating data between the restrictive segments and the flexible segments. So whenever we need to trigger a migration, we trap into the OS. The OS uses the DMA engine to trigger the migration between the flexible segment to the restrictive segment. The most interesting part, how do we use this sort of techniques in the address translation pipeline, in the memory management unit? So there's a new restrictive walker that enables address translation for pages residing in the restrictive segment. It's a specialized hardware circuitry to perform the tag matching and the set filtering. All this stuff that I said before about calculating the hash function, someone needs to do that in the hardware. This way, what do we avoid? We do not need to stop the world and say, oh, I need the OS to resolve the address translation for me. I can do it directly in hardware. Second, we have very small caches for the tag array and the set filter. And this way, we're trying to exploit any temporal or spatial locality from these data structures, which might be very small in size. And third, we do minor modifications in the address translation pipeline. For example, in this scenario, the restrictive segment walk occurs in parallel to the TLB axis, which I will describe. This is the restrictive segment walk. There is an FSM, imagine a Verilog style FSM, that basically is an RTL level style FSM that generates the tag and the set filter addresses based on the virtual address. And then we probe 2 caches at the same time, the tar cache and the chef cache, the set filter cache and the tar cache. These are 2 SRAM structures that store the recent tar and chef entries. And if we miss in these, we need to retrieve the tag array or the set filter from the cache hierarchy and the main memory hierarchy. than the main memory. How does this look in the MMU? After we miss in the L1 TLB, we do two operations in parallel, the restrictive segment walk and the L2 TLB access. If we have a miss in the L2 TLB, we need to wait for the restrictive segment walk result before we start the flexible walk. Let's see the first scenario. We have a page that resides inside the restrictive segment. So this is the physical memory. In this scenario, we perform the L2 TLB access and the restrictive segment walk in parallel. We miss in the L2 TLB and we stall, and we wait for the result from the restrictive segment walker. Oh, data is there. It's in the restrictive segment walker, so we can abort basically the flexible segment walk. So what is the hidden overhead here? That whenever we miss in the L2 TLB, we need to wait for the restrictive segment walker. But as I show in the paper, this is not a big deal. The second, the page resides in a flexible segment. This is the scenario. This is the memory mapping. So in this scenario, we miss in the L1 TLB again. We miss in the L2 TLB, and we stall. But in this scenario, the data is not inside the restrictive segment. So we wasted cycles waiting, while in fact we could perform the flexible segment walk in parallel. And here there is a small overhead which is hidden for stalling in the TLB. In the case of a TLB hit, things are very straightforward. We hit in the TLBs. We don't care about any sort of walk that might happen in the system. When the restrictive segment walk finishes, the data will be stored normally in the TLBs, and we will hit. We don't need to perform any sort of walk. In this scenario, if we hit in the L2 TLB and we trigger the page restrictive segment walk, we would simply abort it. We do not need to continue it. In terms of area and power overhead, we did some comparisons with a high-end Intel Raptor Lake processor using the MacPath tool. And we saw that Utopia incurs a 0.64% area and 0.72% power overhead per core. In terms of evaluation results, we used the Sniper multi-core simulator. We extended it with many features. And I'm going to talk to you about this later. It's already uploaded on GitHub, and we'll give more details on the structure of the simulator. And we used many data-intensive workloads for 500 million instructions. What did we evaluate against? We have 4 comparison points. The baseline system. We have a system that uses a very large software-managed TLB. I will explain what's a software-managed TLB in the next paper. We have the state-of-the-art hash-based page table, the elastic cuckoo hashing. We have a scheme that uses very fast address translation by enforcing a contiguous mapping between the virtual and the physical addresses, so that you can calculate with a single offset the physical page. Utopia with 2 segments, 512 megabyte segments, and a scheme that uses a perfect L1 TLB, so that we see how close is Utopia to an Oracle study where we'd always hit in the L1 TLB, in the L1, yeah. These are the performance results. In the y-axis, you can see the speed up over the baseline system across all the configurations. And as you see, Utopia performs the second best performing scheme, which is the contiguity-based translation, by 13%, and the baseline scheme, the radix-based page table, by 24%, which is a very significant result. Utopia's performance, which is the most interesting one, is that within almost 95% of the perfect TLB. Where does this performance speedup come from? From reducing translation latency. So Utopia reduces the average translation latency by 63% over radix and 14% over the redundant memory mapping score. And what about memory interference that I talked in the beginning? So in the y-axis, we show the normalized DRAM row buffer conflicts of the baseline system compared to all the schemes. And we demonstrate that with Utopia, you can reduce the row buffer conflicts by 20%, 9% less than what the perfect TLB achieves, which means that with Utopia, you could basically use it not just to accelerate other translation, but to also not hurt the locality that you might find in the DRAM when other processes are running at the same time. There are many more results and details in the paper. Sensitivity across different hash functions, parallel and serial TLB access. So with respect to this, yes, there's a trade-off. You could simply do the access serially, which would need less energy. but you would lose in terms of timings, in terms of latency. So you need, it's a trade-off of energy versus a power, let's say, versus latency in this scenario. And we have the results in the paper. The difference is like you lose around, like, I don't remember, I think 2 or 3% of performance, but you gain back something in terms of power. Sensitivity to the restrictive segment size, a reuse level distribution of the 4 kilobyte pages that reside in the Utopia segment, in the restrictive segment. Effect of migration to the memory request, because we're migrating, and I think this is one of the biggest, let's say, drawbacks of Utopia, that we need to migrate pages. The tar and SF cache hit rate, and many more. And you can find the latest version on archive. In conclusion, we propose Utopia, a new virtual to physical mapping scheme that enables both the restrictive and the flexible mapping to harmoniously coexist in the system. Utopia achieves 13% higher performance than the state-of-the-art contiguity-aware translation and 95% performance of an ideal perfect TLB. It's open source, you can find it. It's based on the new simulator. I'm ready for questions. Yeah. There is a chance that this happens. I think timing-wise, I don't think it can happen in reality. The reason is that the L2TLB, let's say, so the L2TLB, you do two things, right? You need to calculate the tag, you access the corresponding set, and then if you have a match, you retrieve the entry. So the tag, let's say, if it costs 2-3 cycles, I don't think in 2-3 cycles you would be able to generate a request. Like, I think it's very tight. But what's the question? Like, okay, let's say that. You can abort it. You can abort it. Because in the MSHRs. Yeah, but it's in the MSHRs, right? Usually. So let's say that you had a miss in the L1. So you would place it in the MSHRs, and then you would simply abort. The same thing can happen in the page. There is a circuitry in the processors right now that can do exactly the same thing to abort a page table walk. So you do not need to wait until the page table walk finishes or something. You can simply abort it immediately. Yes. I'm not sure about the technical details of whether it's indeed eliminated, but you should technically be able to eliminate it. You can design the resources to eliminate it. Yes, you could do. Yes, true. Can we give him a microphone? There's no. There's no microphone here. That's it. Yeah, okay. This one, yes.
Yeah, I think. Okay. So why do you serialize the access to the flexible structure instead of coding all three in parallel?
So because that's where you would basically go into the scenario that the page table walk would generate 4 memory requests, which would make it more complicated to abort them if you hit, right? So it's a much more costly, like this is a matter of power versus latency. You could generate more accesses, let's say in the L1D, L2D, L2 cache, and you might have hits very quickly, right? For the first 2 levels, for example, of the page table walk. So I think it's a trade-off between avoiding the first levels to the page table walk versus getting some latency back, basically. But I agree, we can evaluate this. It's not something that. Yes, exactly. So if you cannot abort quickly, then you would still need to activate the raw buffer, fetch in the caches the data, and it will be a mess, basically. So yes, you would have also this problem. Anyone else before I jump to the next one? I'm gonna be a bit faster in the next one because we know the background now. So. Okay. Okay, now I'm gonna talk about a bit different technique, Victima, how we can drastically increase the address translation rates by leveraging underutilized cache resources. This is my executive summary. So, as I discussed before, address translation is a major bottleneck in data-intensive workloads for two reasons. We have very large data sets and irregular memory access patterns that lead to very frequent L2 TLB misses. Let's say we have a 20 to 50 FPGA misses per kilo instructions, and frequent high latency page table walks. Spend, let's say, 100 to 150 cycles for the page table walks. So what is our motivation? We want to increase the translation rates. What is the translation rates? The memory which we cover by the TLBs of the processor to reduce the page table walks. But if we simply use much larger TLBs, we increase area, power, and energy overheads. So if I simply scale my TLBs, I pay a lot in cost. So the opportunity that we saw is that we can increase the translation rates of the TLB hierarchy by storing the existing TLB entries within the existing data cache hierarchy. So Victima is a new software transparent scheme. There's the OS or the user application doesn't need to do anything to drastically increase the translation rates of the processor's TLB by leveraging underutilized cache resources. How do we do this? We simply transform the L2 cache blocks that contain page table entries. We fetch the page table entries. We can transform the blocks that contain the page table entries into TLB entries. And we do this so that we can directly access the caches using the virtual address and get back the physical one. What are the key benefits? It's very efficient in native and virtualized environments, fully transparent to application and operating system software, and it's compatible with huge page schemes. Victima outperforms by 5.1% the state-of-the-art TLB design and achieves similar performance to a very fast, optimistically fast, 128K entry, which is extremely large L2 TLB. The code is also open source. Background. I will not dive into the background. I will just give you the motivation and the overheads. So in this example, we see the number of occurrences of different page table walk latencies. And as you can see, the page table walk latency is on average 137 cycles. So the core needs to spend so many cycles to perform the page table walk in the radix, in the baseline system. So we have high latency page table walks and frequent page table walks, which lead to very high performance overheads. What is our goal in this work? We want to reduce the page table walk frequency by increasing the address translation rates inside the processor. Let's see what does the address translation rates means practically though. This is a definition. So it's the amount of the virtual address to physical address mappings which are stored by the processor's TLB hierarchy. So an example processors store around 3 to 4 gigabytes of worth of translations by storing both 4 kilobyte and 2 megabyte entries when they're using 2 megabyte large pages. We want to make this much larger. We want to basically increase the reach to reduce the page table walks. One straightforward technique, which we're going to make the hardware TLBs much larger. So in this example, we demonstrate the L2 TLB MPKI in two configurations. The conventional L2 TLB, 1.5 kilo entries. That's what a modern processor has, modern Intel processor. And the second configuration, a 64 kilo entry L2 TLB, which is a very big L2 TLB. If we employ the 64K entry L2 TLB, we can effectively reduce the MPKI from 39 to 24, which is very good. Okay, we're good. We can reduce this. Let's see right now, what do we get back in terms of speed up? So in the y-axis, we saw the speed up over the baseline system, again for the same configurations. And we assume that for the very large L2 TLB, we have a very optimistic access latency of 12 cycles which is not realistic, basically. We keep the L2 TLB latency the same, regardless of whether we change its size. So we see that if we use this optimistic access latency, we can provide 5.4% speed over the baseline system, which is very cool. But the benefits, this sort of benefits do not come for free. If we use a realistic latency, which might be 39 cycle access latency to access the L2 TLB, then this provides only 0.8% speed up over the baseline system, which means that simply increasing the L2 TLB size is not worth it, probably. A second solution, we can use large software managed TLBs. What is this? Whenever we miss in the L2 TLB, we use as a backup a third level of TLBs, which is stored in the main memory. We reserve a contiguous space in the main memory as a cache, as a software TLB. However, this leads to the following problems. High latency. We need to access the memory to retrieve the translations. Second, it needs contiguous physical allocations. We cannot split the software managed TLB across the memory. And third, we need to modify the OS to handle coherence between the large TLB, software managed TLB, and the L2 TLB. Replacement policies, how we can evict from the L3 TLB. And this is very complicated. So we see that both these approaches come with major drawbacks. And our opportunity is to leverage the caches. So we want to store TLB entries in hardware caches. How does this work? Have the MMU, and the MMU somehow needs to store the TLB entries in the L2 cache. So next time we have a miss in the L2 TLB, we do not perform a page table walk. We want to avoid this. We go to the L2 cache, we retrieve back the L2 TLB entry, everything's perfect. Where is the benefit from that? The L2 right now has let's say, the L2 TLB has a 12 cycle latency with 1.5K entries, while the 2 megabyte L2 cache fits 30x more TLB entries. One of the reasons being that it has a much higher cache line size and a much lower latency and an okay latency compared to the L2 TLB, which is 16 cycles. And to remind you here, the page table walk takes 137 cycles on average. If we would simply access the L2 TLB, the L2 cache, and we find our translation there, then we would almost have a 10x decrease in the translation latency in the ideal scenario, right? However, what about interference with program data? What if I place TLB entries inside the TLB, then I might have interference with the program data. So this is a breakdown of the L2 data block reuse, and we demonstrate that the L2 cache is heavily underutilized. So as you can see here, the black portion is the reuse 0, which means I fed something into the L2 cache, I don't ever use it again, and I evict it. And more than 80% of cache lines which are fed in the L2 cache face this property. What's the overview of Victima? The goal is to leverage the cache resources to store TLB entries, and we do this to drastically increase the address translation reach of the processor. So the key idea is to repurpose the L2 cache blocks to store clusters of TLB entries. So we have a low latency and high capacity component to back up the L2 TLB. This is an overview of how we use Victima. Upon a miss or an eviction from the L2 TLB, we consult a page table cost estimator, which is a circuitry that answers the question, is this page costly to translate? If yes, then we transform the page table entry block, the block that contains the last level of the page table, into a TLB block. So next time we have a miss in the L2 TLB, we simply access the L2 cache using a low latency, and we find our translation there. The benefits: drastic increase in address translation rates. It's fully transparent application and OS software. There's no need for contiguous physical allocations, and it's compatible with huge pages. And this is the detailed design. I'm going to talk about how we modify the L2 cache, how we allocate TLB entries in the L2 cache, and what is the design of the page table cost predictor. We need to do two things. We need to change two things in the L2 cache. First, we need to access TLB blocks using the virtual address directly. Second, we need to perform some sort of tag matching for the TLB blocks. An example configuration is a 1 megabyte 16-way associative L2 cache, and the set index in our example scenario is 10 bits. So first, let's see the structure of a conventional data block. So we extend the metadata of the data block with an additional bit to distinguish between the data blocks and the TLB blocks. So in the case of a data block, the TLB entries bit is set to 0. And the conventional data block stores 64 bytes. What does that mean? We need 6 bytes for the offset, right? And as we showed before, the set index is 10 bytes, 10 bits, and the rest 36 bits is used for the tag. So now let's see the structure of the TLB block. In the case of the TLB block, the entry bit, the TLB entry bit is set to 1. So we use a virtual page number to access the this TLB block. We don't use the physical address anymore. And the TLB block contains 8 page table entries. Why 8? Because each page table entry is 8 bytes, and we can fit 8 page table entries inside the cache line. So basically, these 8 entries cannot be any sort of page table entries. They need to be contiguous in the physical address, in the virtual address space. Thus, we use 3 bits for the offset to select which one of the page table entries we need, and the rest of it is the tag, basically. We also need some more bits for the ASID. What is this? So in virtual addresses, we might have aliasing. So if another process is scheduled and uses the same virtual address, it might be able to access what is the translation of another process. To avoid this, we're using the ASID, which is the address specific identifier, address space identifier, which basically distinguishes between different processes. And this way, we won't access the data, the translation data of another process. How does tag matching happen? We take the virtual address. We ask the question, is the TLB entry bit set to 1? Yes. We compare the tags then. Are the tags matching? Yes. Is the ASID matching, which means, am I the correct process? Yes. Then we simply use the offset to select which one of the page table entries we will load and how we will translate our data. How do we allocate TLB entries in the L2 cache? Now we found out how we can access the L2 cache. In 2 scenarios, on an L2 TLB miss and an L2 TLB eviction. On an L2 TLB miss, we miss in the L2 TLB, we perform the page table walk, we fetch a PTE block, and then we consult the page table walk cost predictor. The page table walk cost predictor says, oh, the page is very costly to translate, so you should transform it into a TLB block. So next time we do the walk, this will not be a problem. Second scenario, or an L2 TLB eviction. What is the key here? What's the key difference with eviction? In the case of an eviction, I do not have a guarantee that I will perform a page table walk. We do not perform normally page table walks for an eviction. So we asynchronously trigger the page table walker to fetch a PTE block, the corresponding PTE block in the cache hierarchy. We consult the page table cost estimator, and then we transform it into a TLB block. And this TLB block right now corresponds to the victim, to the evicted entry from the L2 TLB. That's why the mechanism is called Victima. So how do we do translation then? In this scenario, when we miss in the L2 TLB, we have a hit in the L2 cache, which means that we can simply abort the page table walk. What's the bad scenario? We miss in the L2 TLB, we miss in the L2 cache, and in this scenario, unfortunately, we need to pay the price of performing the page table walk. And what about the design of the page table walk cost predictor? So its objective is to predict which pages are costly to translate and insert only those inside the L2 cache. How do we track this? It's the same mechanism as Utopia. We embed counters inside the page table entry for the frequency and the cost of the page table walk. Upon a page table walk, we update these counters, and we use a page table walk cost predictor that takes these 2 counters into account. And using a comparator tree, we find out whether this page is costly to translate or not. However, if we find out that the L2 cache is so underutilized that it doesn't matter whether we need to make an intelligent decision, we simply place everything inside the L2 cache without taking into account any sort of metrics from the page table walk process. There are more details in the paper, like we did some feature engineering to decide to find a minimal set of useful features. And we ended up with a two-feature comparator that predicts costly to translate pages with a 2% accuracy. So we took into account first multiple features, and we did some feature engineering. So basically, we came up with much bigger neural networks in the beginning to make a very highly accurate prediction. For example, we had the biggest neural network makes a prediction, makes a 10% more accurate prediction. But we find out that, okay, we can simply lower a bit the accuracy while keeping the overheads in a much lower, the area and the power overheads. So we find out at the end the two-feature comparator predicts the cost to translate pages with 82% accuracy with much lower overhead, for example, using a very big neural network. We also employed Victima in two-level address, in virtualized environments where we need to do a two-level address translation. We have guest virtual, which is running on the host machine, and the host machine is using virtual addresses which need to correspond to the host physical addresses. So we have two levels of address translation. In this scenario, we do something very simple. So in the system right now, there are two TLBs, an L2 TLB and an nested TLB. The difference is that the nested TLB stores translations from the guest virtual to the host virtual and not directly from the guest virtual to the host physical. And we do a simple thing. We just simply spam the L2 cache with translations from the nested TLB and the L2 TLB. And this way we can accelerate both of these at the same time. These are the evaluation results. Again, we use the same evaluation infrastructure, same workloads, and we find out that we use these configurations, the radix page table with both 4 kilobyte and 2 megabyte pages, an optimistic L2 TLB with 64 kilo entries, optimistic L2 TLB with 128 kilo entries, the state-of-the-art software managed L3 TLB, and Victima. And we found out that Victima achieves similar performance to the optimistically fast 128K L2 TLB, which is the most significant result in the page. Where does this come from? It comes from the reduction of the page table walks. So Victima can reduce the page table walks by 50% on average compared to the baseline system because of the very high reach in the L2 cache. What's the effect of the L2 cache size on Victima? We basically show the reduction of the page table walks as we scale the L2 cache size from 2 megabytes up to 8 megabytes. And we show that employing an 8 megabyte L2 cache with Victima reduces page table walks by 63% compared to a scheme that also uses an 8 megabytes without Victima. And in virtualized environments, we use some state-of-the-art schemes, and we also demonstrate that Victima outperforms the 64K entry software managed TLB that I talked about before by 12%. In terms of area and power overhead, the same comparison with MacPath against an Intel Raptor Lake. These are much lower than Utopia's performance and area overhead because it's a mechanism that does not require significant additions to the core microarchitecture. There's much more in the paper, how we integrate in the virtualized environments, how to do maintenance operations like TLB shutdowns to keep the TLBs coherent. We have a new replacement policy to intelligently handle the evictions and the replacements for the TLB blocks. And we have also implementation details of the page table cost estimator. You can find all these in the archive version. It's also open source. We received the Distinguished Artifact Award at Micro. You can replicate the results. And I also have some documentation available, whoever wants to extend the mechanism. In conclusion, we presented Victima, a new software transparent scheme that drastically increases the address translation of the processor's TLB hierarchy by leveraging the underutilized cache resources. And the key idea is to transform L2 cache blocks that store page table entries into blocks that store TLB entries. And Victima outperforms by 5.1% the state-of-the-art software managed TLB and achieves similar performance on optimistically fast 120K, 28K entry L2 TLB design without the associated area and power overheads. Code is open source, you can play around with it, and I'm happy to receive questions. Anyone? This was much simpler, right? How much time do I have? Can I take 10 minutes? Okay, sure. Okay, so I'm gonna talk right now about Virtuoso. It's a work under submission. So it's how I can enable fast and accurate virtual memory research with an imitation-based OS simulation methodology. It's based on a micro SRC poster, which we submitted last year with Konstantinos. The other one, not me. So we want to, basically our main solutions which try to improve virtual memory. And these overheads of virtual memory are deemed to increase when we transition to much larger physical address spaces. The virtual data sets become much larger. And as I show here, there are two interesting results. So we have two clusters of applications, short running applications. We have LLM inference, we have serverless workloads, we have matrix operations that spend 30% of the execution time on minor page faults, which means they spend 30% of the time on allocating memory, just allocation, no address translation, just allocation. And we have, on the other hand, long-running workloads that spend 27% of execution time on address translation and 5% of time on memory allocation. So we have two overheads here of virtual memory. One is the memory allocation overhead, and the other one is the address translation overhead, which appear in different sort of workloads. So we try to co-design the OS and the hardware to avoid all these problems. We use software-managed TLBs, employing large pages. We employ contiguity to solve the address translation problem. We try to rethink how page tables work. We add hardware support to handle the allocation in the hardware. We try to use Utopia to employ much better address mappings and accelerate address translation and reduce the interference in the memory hierarchy. However, if we want to really effectively evaluate these virtual memory techniques, which is very crucial for progress in the domain, what are the evaluation requirements? We have interdependency between components. So what does that mean? We have OS management, which is running the software. We have a hardware MMU, and we have other system components like a DRAM, for example. And they are all connected to each other. The way we allocate 2 megabyte pages, whether it's going to be aggressive or not, will change how the hardware MMU, what's the effectiveness of the hardware MMU, which will change how many requests am I going to send to DRAM to perform the page table walk. An example, the TLBs, they live and die based on the memory allocator based. So the performance of the TLB heavily depends on whether the page allocator can provide 2 megabyte pages or not. If the page allocator can provide 2 megabyte pages, everything is perfect. We have a very high reach in the L2 TLB. If not, then we start tanking performance because we send requests for the page table walks in the memory hierarchy. Someone else came up with a new page table design. They figured out that it has very low latency. It's like the fastest page table walk, but it causes very high interference in the memory hierarchy, which means that even though we can, let's say, send 100 requests in parallel for each page table walk, and we can get back the translation very fast, we destroy everyone else's performance. What's the problem with existing simulators that try to evaluate the overheads of virtual memory and evaluate such solutions? They're very slow or very hard to develop. One class of these simulators, like Cramulator, Sniper, Chamsim, that Rahul is using a lot, they focus on microarchitectural features that do not support OS-level interactions, and they use first-order models to basically approximate the virtual memory overheads. So what is a first-order model and why we shouldn't use it? It's a static timing model, basically. You have a heuristic, you have an equation that basically gives you the page table walk latency or the minor page fault latency. And in most of these simulators, it's a fixed number. So let's say for every page table walk, we're going to charge 200 cycles. For every minor page fault, we're going to charge 2,000 cycles. An example, though, that contradicts this choice is, in the y-axis, we show the average page table walk latency across 45 diverse stress benchmarks. And these are come from a real system. And we show that the page table walk latency can range from 20 cycles in a real system up to 100 cycles. So how can you determine, using a static model, what should be the page table walk latency? Same thing for the minor page fault latency. In this example, we enable transparent huge pages, we disable transparent huge pages, And we saw much different behavior in the amount of outliers in terms of the minor page fault latencies. And we see that the latency of the minor page faults is highly variable. We cannot just keep it to a static number. What's the problem, though, with full system simulators right now? There are a class of simulators which are full system. We can run an operating system on top of them. They're very low in speed. If someone has worked here with Gem 5, for example, you would have already seen that it takes ages to execute in the full system mode. They're very hard to develop. I mean, that's a subjective argument, but if anyone has worked with Gem 5, again, they can confirm that it's harder to develop than Samsung, for example. It's also very hard to debug. It takes time to boot the operating system, for example. If you change something in the operating system, you need to reboot the simulator every time. In this example, I show the debugging flow over here. This is some results which we got for our submission. And we demonstrate that to perform a debugging cycle, which means I simply compile and run. It takes 23x more time in Gem 5, which is a full system simulator compared to an emulator. In the emulator, I can compile a simulator. I change, let's say, one file in the simulator. One of the, let's say, high order header files, which is the main file of the simulator. I compile the simulator, and then I run a small test, and this is 23x faster than doing the same thing in Gem 5, which is, for people who are working with simulators, this is a big productivity, has big impact on productivity, basically. And our goal in this work is to basically design a simulator that can support simulating the operating system kernel, has high speed, high accuracy, and low development effort. So the key idea of Virtuoso is to quickly and accurately prototype and evaluate the software and hardware components of virtual memory. And the key idea is to employ a user space lightweight kernel to isolate the desired functionality of the OS code, easily develop new OS routines, and evaluate the microarchitectural implications of the operating system. The key mechanism, I'm using a simulator here as an example. It's a Sniper multi-core simulator, which we started building Virtuoso on top of. We have a user space kernel, which is called Mimic OS, that enables ease of development. We can write our modules in C++, let's say, that basically mimic what the operating system would do to implement transparent huge pages. So when we have a page fault, let's say from the multi-core simulator, we dynamically instrument the code of the user space kernel, and we inject the instructions again back into the architectural simulator. This allows us to simulate what the operating system would do in case of a page fault. We also use the same mechanism to provide the functional updates. Do I allocate a 2 megabyte page or a 4 kilobyte page? So we have these benefits at the same time. With Constantinos, we basically built some sort of the Linux subsystem inside Mimic OS. So we can handle, let's say, the allocation, we can handle HUDCL BFS, different mappings, the installation of the page table process. And this way we show that someone can easily do it with a much lower effort compared to changing the actual Linux kernel. We also built Virtual, which is a comprehensive tool set that contains multiple hardware OS co-design virtual memory techniques to enable further research. You can find it more we can find it in the paper. And we integrate the Virtuoso with 4 simulators. The emulator, Sniper, Samsim, and the Gem 5 version doesn't use full system execution. It uses a system called system call only execution mode, where you don't actually simulate the whole operating system. We validated with different metrics, the L2TLB, MPKI, the page table walk latency, similarity in allocated pages, the minor page fault latency. And we demonstrate that 95% of the allocated pages are the same between VirtuoS and Linux, which means that they can basically allocate in the same way the pages. And in terms of the L2TLB MPKI, which is one very interesting component, we see that we have accuracy within 93% compared to a real system that has a high-end server, basically. So we compare the L2TLB MPKIs, and we see that Virtuoso can achieve 93% of the actual accuracy. We also compare the page table walk latency, and we find out that the accuracy of Virtuoso is within 92% compared to the page table latency, which we observed from a real high-end server. And we also compare it against other state-of-the-art simulators. And we see that it's 6x faster than the Gen 5 full system, while accurately simulating a Linux-like operating system. It's also open source. We are trying to keep up with some updates. Haven't released them yet, but we will. And some example use cases. We evaluated different page table designs, for example, in the paper, different hash-based page table designs. We demonstrated that, as we decrease the memory fragmentation, the speed up of different page table design changes. So if we provide more aggressively more 2 megabyte pages, then the different hash-based schemes have different speed ups. In terms of minor page fault latency, we show that using the state-of-the-art hash page table, we have much higher minor page fault latency because of the way it handles collisions, because it's a hash-based page table. And we also show that the elastic cuckoo hash table leads to 52% increase in DRAM buffer conflicts, which is the overhead I talked about before, that it's very fast, it's faster than the baseline, but it causes much higher interference. Some other use case, we show the translation latency. We show that we can do comprehensive comparison against different state-of-the-art MMU designs. And we also integrated with MQSIM, and we demonstrate that if we use a very large restrictive segment in Utopia, which means it covers, let's say, 90% of the total memory, we increase the swapping activity because the flexible segment might be filled up with entries. Your restrictive segment is extremely big, and you have some conflicts in the restrictive segment, but your flexible segment is full. So you cannot place the data anywhere else than the swap space. And if you go above 90%, let's say, then you start observing very high increase in cycles to do swapping. And we did some more studies with intermediate other spaces, which are I do not need to discuss right now. So in conclusion, Virtuoso provides a fast and accurate methodology to conduct virtual memory research, and it's a promising start for establishing a common ground for virtual memory research. You can find it on GitHub, and you can play around with it. And we're basically right now working actively on it and integrating more features. I don't think you have questions, so I will jump directly to the to the challenges going forward in the topic. So we need to design more efficient data structures to store the page tables. That's the one way you could approach it. It would be good to co-design data placement and address translation. How can we design a mechanism that intelligently places data in the main memory to perform very fast address translation? How can we also handle the interference between data and the metadata intelligently? There are two works that recently proposed how to design more efficient data structures to store the page tables. One in ASPLOS 2020 and one recent one in Micro 2024 that also used Virtuoso to perform its evaluation. What is the problem with elastic cuckoo hashing? What I described before. We have multiple hash tables. That's why it's called cuckoo, multiple nests. And if we do not find, we need to perform 3 accesses in parallel, which means that if we have 2 collisions in the first 2 hash tables, we will resolve our translation process at the third one. But what does this cause? Multiple parallel memory accesses. And as I showed before, we have 50% more buffer conflicts compared to the baseline system, which gives us a lot of headroom to optimize it. So it's not only about the performance you're getting out of it, it's also about what you're causing to the system. Another challenge, we can co-design data placement and address translation. As I said before, we can restrict the virtual address to physical address mapping. And as I said, so this leads to much smaller translation structures. But we need the contiguity because the segment in Utopia, the restrictive segment, needs to be contiguous. We cannot hash anywhere we want, right? And we need to size it. We need to choose a size for it. We need to migrate data. And this is something that we want to avoid ideally. We can enforce though contiguous virtual to physical address mappings. This way we can do very fast translation because we enforce the contiguity and we simply calculate with an offset the physical address. At what cost though? Because this heavily depends on the fragmentation in the system and the available contiguity. If we don't have contiguity, this cannot be enabled at all, right? And third, like the question is, can we enable any other microarchitectural optimization by using intelligent mapping? And this is something that I'm very interested on and I'm working on it right now. Third, how we can handle interference between data and metadata intelligently. We have a larger L2 cache, and the L2 cache will become a lot larger in the future. And the question is, okay, right now my data in the L2 cache might experience some locality because the L2 cache is very large. So the question is, when the data and the metadata, the page table data, start competing with each other, how do we intelligently handle the resources so that we can, at the same time, perform fast address translation and do not destroy the data accesses? Again, this is another problem, the memory allocation overheads. We have more than 30% of our average execution time which is spent on allocating memory. Why? We have a very complex and high latency pipeline in the operating systems right now for allocating memory, which cause frequent context switches. What does this mean? When we have a fault, we context switch to the OS handler, and whichever instructions in my program were ready to execute, they cannot execute. They need to face bubbles. And they stall until the OS handler finishes its execution. So what does that mean? That the context switching back and forth from the OS to the user space kills the instruction level parallelism. I cannot execute my instructions in parallel to what's happening in the operating system. We also have emerging computing systems, like we have multiple computing devices, GPUs, host CPUs, AI accelerators, PIM-enabled devices, which you have seen in the course, and they all have heterogeneous memories. The GPU, for example, has a very fast, small memory. The AI accelerator has a specialized memory buffer for the weights. The PIM-enabled module might be, let's say, has a more power-consuming memory. And the host CPU has a very large, let's say, but slower memory. And they all communicate in the system with each other. So the question is, how can we orchestrate memory management in a holistic manner? And an example is the GPU-CPU interactions, right? The GPU has a high bandwidth limited capacity memory. And to be able to fit more clients inside the GPU, what they're doing right now is they oversubscribe the memory. What does it mean? We place GPU data inside the CPU memory, and we treat those two memories as a unified virtual memory. And this enables basically transparent memory over subscription. If you're interested in the topic, you can check the theses which are uploaded on the website. And you can, of course, reach out if you have any potential discussion and ideas that you would like to pursue. Thanks a lot for your attention. If you have any questions. We'll have a 10-minute break.
Hello, hello. Can you hear me? Hello. Hello. It's not, it's good. Okay. Okay. Hello again, everyone. We don't have that much time, so I'll try to be quick. So don't judge me on that. So I am Ismail. I'm a PhD, first year PhD student here. And my research interests are computer architecture, as everyone else, processing in memory and DRAM safety, security, and reliability, and more. So I'll start with first DRAM Bender. A very quick summary. I believe you already know what DRAM Bender is. And then I'll jump into the two works that I did this year for about processing using real DRAM chips. First one will be the functional complete Boolean logic in real DRAM chips that we call FCDRAM. And the second one is simultaneous manner of activation in real DRAM chips that we call for short SIMRA-DRAM. So let's quickly start with the DRAM Bender. So this paper is published in IEEE TCAT in 2023. The DRAM Bender, an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. So why do we need to test DRAM chips, right? So there are a lot of factors that affect DRAM reliability and latency. And we would like to understand the reason and develop a better understanding of DRAM for the factors such as timing violation, cell interference, such as row hammer, manufacturing process, temperature, voltage, and so on. However, the factors that affect DRAM reliability and latency cannot be properly modeled in simulation or analytically. Therefore, we need to perform experimental studies on real DRAM chips. But there are already some existing open source DRAM testing infrastructures that allows us to perform experimental studies, such as SoftMC and LightX test. However, these infrastructures have three key limitations. First, they impose restrictions on DDR4 interface. Restrictions limit various characterization experiments, such as you cannot violate the timing, for example. And the second one will be difficult to set up. So some of them are pretty old, such as SoftMC, so they're based on discontinued hardware or software. And the third one will be the monolithic hardware design, and which makes extensions relatively difficult. So in order to port to another board or another interface, you need to touch a lot of things in that infrastructure. So the DRAM Bender has three design goals. First, flexibility, then ease of use and extensibility. So we would like to test any DRAM operation with any timing parameters, ideally. And then we would like to have a simple programming interface that has minimal programming effort and time. And it should be accessible to a wide range of users. So you don't need, ideally, you shouldn't need to know what's going on in the hardware side, in the RTL side. And the last one is extensibility. It should have a modular design and should have well-defined interfaces between hardware modules. So to this end, proposed DRAM Bender, it's the publicly available FPGA-based DDR3, DDR4, and HBM2 characterization infrastructure, which is easily programmable using the DRAM Bender C++ API. So it already supports 5 out-of-the-box FPGA-based prototypes from like Bitware, AMD Xilinx, that has DDR3, DDR4, or HBM2. And in this paper, we show 3 case studies to show the effectiveness of DRAM Bender. And it leads to 3 new insights. First one will be the row hammer, the interleaving pattern of activations. We see that interleaving pattern significantly affects the number of row hammer bit flips. The second one, the random data patterns, how random data patterns affects the row hammer bit flips. By using 512 random data patterns, we see that we uncover more bit flips than just 8-bit random data patterns that prior infrastructure SoftMC uses. And the last one, which I'll be discussing more, is in DRAM bitwise operations. In the paper, we demonstrate in DRAM bitwise and then OR operation capability in real DDR4 chips. So we believe that DRAM Bender is flexible, that support many different types of experiments. So let's see an example how easy to use DRAM bender. So for interleaving pattern of activations, you see a code snippet here. It shows the one iteration of row hammer test. It's just 12 line, a total of 12 line that enables you to perform row hammer in the real DRAM chip. So we believe this is easy to devise new experiments to uncover new insights. So there are a lot of things in the paper. First will be the design details, the ISA, hardware software modules, prototype design, temperature controller setup. And second, the application like a programming interface, API, detailed results of these 3 case studies that I foreshadow and future work and improvements. And the paper is already on archive, which is extended. And there are a lot of research that DRAM bender enables, which we count up until 33, but there will be more, hopefully. And a highlight will be the FCDRAM, which is a recent paper that we published using this infrastructure, which I'll be talking next. And as a summary, the DRAM bender is the first publicly and freely available DDR4 characterization infrastructure, which is flexible and easy to use. Source code is available if you have any of the let's say, if you have any of the FPGA machines that the DRAM bender supports, you can directly test your real DRAM chips. So we believe and hope that DRAM bender enables many studies, ideas, and methodologies in the design of future memory systems. And it also has, I would like to say that it also has a tutorial video for 43 minutes that Ataberk shows that how you can program the FPGA and test your DRAM chip. And that was a very quick summary for the DRAM bender. If you have any questions, you can get that, or I would like to go to the second one, which is FCDRAM. Yes. Yeah. There's already a file underlying that, so that we don't, let's say, there's already a, how can I say it, a hardware component that already checks the signal integrity that shows us that when you issue it, yes, you issue that instruction. So we have already a lot of debugging opportunity that we can do, as well as in the test bench in the Verilog, and also, I guess, the real-time debugging as well. But I'm not that sure of the second one. Yeah. Any other question? Okay. So the second one is FCDRAM. Functionally complete Boolean logic in the real DRAM chips and experimental characterization analysis, which this paper is published in HPCA 2024 this year. Let's dive into the executive summary. The motivation is that processing using DRAM is a promising paradigm that can alleviate the performance and energy bottlenecks caused by the frequent data movement between main memory and processing such as CPU. And prior works show that existing DRAM chips can already perform 3-input majority and 2-input AND and OR operations. However, these demonstrations on off-the-shelf DRAM chips do not provide functionally complete operations such as NAND or NOR, or NOT operation, and more than 2-input AND and OR operations. In this study, we tested a total of 256 DDR4 chips from 2 major manufacturers, and we observed that off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16-input AND and OR and NOR operations with very high reliability. A data pattern and temperature only slightly affect the reliability of these operations. So here's the outline of my talk. I'll start with a brief background. I believe you already know what DRAM is, but let me refresh your mind. Here we have a DRAM module that has multiple DRAM chips. Inside the DRAM chip, we have multiple DRAM banks, and inside the DRAM bank, we have multiple subarrays and sense amplifiers. Inside the subarray, we have 2-dimensional array of DRAM cells and a row of DRAM cells called DRAM row, and they are connected to word line. A column of DRAM cells are connected to sense amplifiers through a bit line. And in modern DRAM chips, to achieve high density DRAM chips, to pack as much as possible cells inside the DRAM, we have an architecture called DRAM open bit line architecture. Here we have two subarrays, and these two subarrays, neighboring subarrays, share a common source, common component called sense amplifier. Here we have an example over there. In the upper subarray, we have the bit line, and the lower subarray, we have the bit line bar, and they're connected to the same sense amplifier. Upon an activation, for example, we activate the row from the upper subarray, we see that the bit line bar in the lower subarray is not activated and serves as the reference for the sense amplifier. And note that the sense amplifiers consist of back-to-back NOT gates. So after a successful activation, bit line and bit line bar will have the complementary value. For example, bit line will have 1, while a bit line bar having 0. So in this study, we will leverage this component and this operation. So the major DRAM operations that we focus in this study are, first one is that the activate command, which fetches the row content into sense amplifiers. The second, column accesses, which we issue read and write command to target column and drive the data to I/O. And the precharge, which prepare the subarray or generally the bank for a new activate command. So in this study, our goal is to understand the capability of off-the-shelf DRAM chips beyond just storing data and rigorously characterize the reliability of this capability. And in this paper, we show that off-the-shelf DRAM chips can simultaneously activate up to 48 rows in 2 neighboring subarrays, can perform NOT operations with up to 32 output operands, and can perform up to 16 input AND, NAND, or NOR operations. And we, thanks to DRAM vendors, we conduct these experiments in real DRAM chips, which enables us to have a fine-grained control over DRAM commands, timings, and temperature. And we test a total of 256 DDR4 chips from 2 major manufacturers, and we cover different die revisions and chip densities, basically different DRAM architectures as well. And our testing methodology is we focus on neighboring subarrays and, of course, shared sense amplifier between them. And we use a key command sequence called activate row A, precharge, and activate row B, where row A is in subarray X and row B is in subarray Y. And we carefully sweep these row addresses to cover all rows in their subarray. And we sweep the timing parameters between each command in this command sequence. So now let's take a look at our first finding, multiple row activation in neighboring subarrays. So the key observation is that activating 2 rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. So here again, we have this pictorial example, and we have our key command sequence. When we respect the timing parameter, we will activate only 1 row at a time. However, if we violate this timing greatly, we observe that we can activate multiple rows in 2 neighboring subarrays. To understand which and how many rows are simultaneously activated, we sweep row A and row B addresses to cover all rows in their subarrays. So we observe that off-the-shelf DRAM chips have 2 distinct sets of activation patterns in neighboring subarrays. First one is exactly the same number of rows are activated in each subarray. We observe that we can activate up to 16 rows in each subarray, a total of 32 rows. And the second pattern is that twice as many rows in one subarray are activated compared to its neighbor subarray. We observe that we can activate up to 16 rows in one subarray while activating up to 32 rows in its neighbor, a total of 48 rows. So we conclude that off-the-shelf DRAM chips can simultaneously activate 48 rows in 2 neighboring subarrays. I'll give more details in the next paper that how we activate multiple rows and why we activate that. For that, please stay tuned. And now let's move on to our first Boolean operation, which is the NOT operation. So the key idea is to use the connection between neighboring subarrays, the NOT gate and the sense amplifier. Here we have 2 source and destination cells, which are in the neighboring subarrays. The key idea is that connect rows in neighboring subarrays through a NOT gate by simultaneously activating them. So now we activate source first, which will drive its value to its bit line, and the complementary value will be driven to the destination's bit line. And then if we activate destination without deactivating the sense amplifiers or precharging the bit lines, we will store the negated value of the source in the destination. Now let's see this operation at lower abstraction level. Here we have source and destination. They initially have the voltage value of ground, which is 0, and bit lines are precharged to VDD over 2. First, we issue activate source, which will connect source to the bit line. And we wait for nominal timing parameter, which will drive its bit line to ground and drive the destination's bit line to VDD. And then we issue back-to-back precharge and activate command with violated timing parameters. What will happen is that we first connect the destination to bit line. And since we interrupt the precharge process, what happens is that sense amplifier is still enabled and the destination's bit line is still in VDD. As a result, after waiting long enough, the negated value of the source is written to destination. So to characterize this operation, we again sweep the row A and row B addresses, and we sweep the DRAM chip temperature from 50 degrees Celsius to up to 95 degrees Celsius. And to evaluate the reliability of NOT operation, we propose a metric called success rate for a DRAM cell, which is the percentage of trials where the correct output of a tested operation is stored in the cell. So we test a total of 10,000 trials. For example, for this example, we have 4 trials and half of them are correct. And thus the success rate for this cell is 50%. Now we have 3 or 2, I don't really remember, key takeaways from this experiment. First one is off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows. You have question? Yes.
Go back. No, this one's good. So inside one DRAM subarray, there's 512 rows or even more, right? And only
yes.
And only 32 rows from these 512 selections are able to do this operation, or?
No. So we observed that we can activate up to 32 rows simultaneously in performing act per act because of the row decoder, how row decoder circuit works. So we can use any of the 32 rows, but at a given time, we can only use 32 rows because we can activate up to 32 rows.
What do you mean by activating 32 rows? We're doing NOT operations, right?
Yeah, for NOT operation, what we do is we first activate one row, right? And then we activate multiple rows in neighboring subarrays so that we propagate the negated value to the neighbor. So you can activate only one row to perform the NOT operation, or you can activate up to 32 rows. So in order to negate, let's say, the value to 512 rows, we need to activate 512 rows at the same time.
Okay.
So here, let me go back. So here, assume that we just activate destination cell. If we have just one cell, we will just negate one value, right? So the source, negated value of the source will be written to one destination cell. But if we activate, I don't know, 512 rows, which means that on that bit line, 512 cells will have the negated value. But our experiments show that we can activate up to 32 rows while activating 16 to its neighbor. We conclude that we can negate the value to up to 32 output operands.
Up to 32 simultaneously.
Yes.
But we can write to the destination in any of the other rows in the other subarray.
It's not in one shot, basically.
Okay.
You can do it repeatedly.
Okay.
Basically, we test I believe 6 subarrays in a bank, and we test all banks. And in that subarray, we test all the cells. And I'll show you the results as a distribution. But that was a good question. Thank you. Do we have any questions? So it's like row clone, yes. Can we do NOT operation in any rows inside a subarray? Or should it be in a specific row? No, it can be any row, hopefully. It depends on the row decoder circuitry you have in the DRAM module, but it's similar to row clone. So we observed that in the row clone, you can have any of the row as source or any of the source as destination. In here also, in most of the models, we see that you can have this opportunity. It depends on the timing parameter you use when you violate. So here it's 3 nanoseconds, right? In some of them, you need to have 1.5 nanoseconds. In some of the models, you need to have 4.5 nanoseconds, blah, blah. So it depends on the DRAM model, like row decoder circuitry you have. But we observed that we can test all of them, at least in our tested models. Okay. Any more questions? No? Okay, I'm moving on. Where was I? Okay. Our first key takeaway from this experiment is off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows, and temperature has a small effect on the reliability of NOT operations. So now let's take a look at our first result. Here in the x-axis, we have the number of destination rows. In the y-axis, we have the success rate distribution across DRAM cells that we tested. And our observation is that there is at least one DRAM cell that can perform the NOT operation with 100% success rate across all tested number of destination rows. As a result, we conclude that off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows. So now let's take a look at the impact of temperature. We use destination cells that can perform NOT operation with more than 90% success rate at 50 degrees Celsius to keep the experiment time reasonably. And we observe that there is only 0.2 variation in average success rate when we increase the temperature from 50 degrees Celsius to 95 degrees Celsius. And we conclude that temperature has a small effect on the reliability of NOT operations. And now let's move on to the last demonstration, AND, NAND, or AND NOR operations. So here, the key idea is that manipulate the bitline voltage to express a wide variety of functions using multiple row activation neighboring subarrays. Here we have 4 cells, 2 of them from upper subarray and 2 of them in the lower subarray. And as you can see, when we precharge the bank, we precharge to a certain value, which is VREF. And when we activate a single row, let's say from the upper subarray, the lower subarray's bitline is still at VREF, right? And that's why we can perform read and write operations. So when we activate multiple rows in neighboring subarrays, what happens is that those bitlines becomes the function of activated cells value, such as the upper subarray's bitline becomes the voltage value of A and B, and the lower subarray becomes the voltage of X and Y, which is the function is the average, actually. And sense amplifiers compares the average of A and B and X and Y to determine which one is higher or lower. So now let's see how this key idea works to perform 2 input and then NAND operations. Now we have 2 subarrays. From top we have reference subarray. The bottom we have the compute subarray. At the top we have 2 cells, which are VDD and VDD over 2. We can store VDD over 2 thanks to a prior work. And the compute subarray we have 2 cells which have the voltage value of X and Y. Now assume that when we issue act per act sequence, very quickly, we activate these 4 cells simultaneously. What happens on those bit lines is that they become the average of activated cells, right? So for these examples, reference bit line becomes the average of VDD and VDD over 2, and compute bit line becomes average of X and Y. Now let's see how we construct a truth table from sweeping the input values for X and Y. The first case will be where X and Y are both 0, which is ground. Now the average for the reference bit line is 3 VDD over 4, while compute is ground. But sense amplifier will compare the voltages on the bit line. Since 3 VDD over 4 is higher than ground, reference subarray cells will have VDD, while the compute cells will have ground, which is compute as 0, reference is 1. And now the second case, where X is 0 and Y is 1. Now the compute bit line have the voltage value of VDD over 2, but this still is lower than 3 VDD over 4. And the result is the same. Reference subarray will have 1, compute subarray cells will have 0. And for the third one, where x is 1 and y is 0, the output is the same, right? The average is still VDD over 2, which is still lower than 3 VDD over 4, and the result will be the reference subarray will have 1 and compute subarray will have 0. So for the last case, where x and y are both 1, now the compute bit line voltage is greater than the reference bit line voltage. And as a result, reference subarray cells will have 0, while the compute cells will have 1. Now, by doing that, we can realize that compute subarray cells will have the AND operation of x and y, and at the same time, reference cells will have the NAND operation of x and y. And to be able to perform many input AND, NAND, OR, and NOR operations, the key idea is really carefully manipulating reference voltage. Here we carefully use VDD and VDD over 2, right, in the reference voltage. So you can play with that to realize OR and NOR operations, and you can scale this to n number of inputs. For this one, please check the paper for more details. But if you have any questions, I can put the answer. Yes.
So this really depends on the fact that both the two sides of the sense amplifier, that is the two subarrays, have the same type of cell. That is, both are either true or anti.
So yes, so we observed that Samsung and Hynix both have all true cells, and yes, they should have all true cells so that we can store if it's 1, if it's 1.
If it's like
if it's anti-cell,
true and anti, because you're sharing a sense amplifier across 2 bit lines.
Yes.
You should have a true and anti, right?
No, it depends on the design choices.
Okay.
So there are a lot of ways of designing DRAM for true and anti cells. And actually, in the tested DRAM modules for Samsung and Hynix, we observed that they're all true cells. So they switch, they use that switches in somewhere else. But in Micron, for example, it's one of them is true, and another one is anti, the other one is anti. So yes,
it's possible to basically
yes
design in a way to support this.
Yes, yes, it's definitely possible. Any more questions? No? Okay. So that was it. And the characterization methodology is the same as before. We sweep row A and row B addresses to cover all the rows. And we have 3 key takeaways. First one, off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations. And off-the-shelf DRAM chips can perform AND, NAND, OR, and NOR operations with very high reliability and data pattern slightly affect the reliability of AND, NAND, OR, and NOR operations. And now let's take a look at the first result here. In the x-axis, we have the number of input operands. In the y-axis, we have the success rate. And the hue, each colored box shows the operation AND, NAND, OR, and NOR. And here we observe that off-the-shelf DRAM chips can perform 2, 4, 8, 16 input AND, NAND, OR, and NOR operations. And for the 16 input, they can achieve, off-the-shelf DRAM chips can achieve very high success rates. And now let's look at the impact of data pattern for specific for NOR operation. Yes.
Is there any specific reason that why OR and NOR had slightly higher success rate than N and NAND?
So one hypothesis could be the sense amplifier could be biased towards to, for example, 1. And in the OR case, in the truth table, let's say for the 2 inputs, assume that most of them are 1, right? So if your sense amplifier is biased towards the 1, so you will have more, let's say, correct results. Because in AND, most of them are 0. So it's because of how sense amplifier works. Because it's not designed for this purpose, actually. So it's even surprising that they have this much of a success rate when you think about it, because sense amplifier just operates with just 1 row at a time. But now in 2 terminals of sense amplifier, we're, let's say, stressing them, right? By activating multiple rows. But that was a question. So, okay, now I'll move on. Now, for the impact of data pattern, each colored box shows a different data pattern. The purple one is all ones and all zeros, which we initialize the row with all one or all zero. The other one is random, which we initialize the row with just random values. So we observe that there is a less than 2% variation in average success rate across all tested number of input operands, and this trend is consistent across all tested operations. And we conclude that data pattern slightly affects the reliability of AND, NAND, or NOR operations. Okay, there are a lot more content in the paper, such as detailed hypothesis and key ideas to perform NOT and many input AND, NAND, or NOR operations, and how the reliability of bitwise operations are affected by the location of activated rows, basically the distance to the sense amplifier, and the temperature, DRAM speed rate, chip density, and die division. And lastly, we discuss the limitations that we face when we test real off-the-shelf DRAM chips. Our paper is available on arXiv and actually open source in GitHub, but I forgot to include that slide, so you can find it. And let me conclude my talk for this paper. So we experimentally demonstrated off-the-shelf DRAM chips can perform functionally complete Boolean operations up to 16 input AND, NAND, or NOR operations. And we characterize the success rate of these operations using 256 DDR4 chips from 2 major manufacturers. And we observe that they can perform NOT and 2, 4, 8, 16 input AND, NAND, or NOR operations with very high success rates, and data pattern and temperature only slightly affect the reliability of these operations. And we hope and believe that these empirical results demonstrate the promising potential of using DRAM as a computation substrate. And that was FC DRAM. Do you have any more questions? Not. How much time do we have? Let me check. 15. Okay. I'm going to speed run. Sorry. So the next paper is Simra DRAM, simultaneous many row activation in off-the-shelf DRAM chips and experimental characterization analysis. This was published in DSN 2024 this year again. So let's jump into executive summary. The motivation is still the same: processing using DRAM elevates data movement bottlenecks, but off-the-shelf DRAM chips are limited to 3 input measured and in DRAM copy operations. So our goal is to experimentally analyze and understand the computational capability of off-the-shelf DRAM chips beyond that of prior works, and the robustness of such capability under various operating conditions, such as temperature, voltage, data pattern, etc. And for this paper, we test a total of 120 DDR4 chips from 2 major manufacturers. And we observed that off-the-shelf DRAM chips can perform MASH 5, MASH 7, and MASH 9 operations, and copy 1 DRAM row up to 31 different rows at once. And we also observed that storing multiple redundant copies of measured these input operands in those, let's say, when you activate many rows, drastically increases robustness, in some cases more than 30%. And operating conditions such as temperature, voltage, and data pattern affect the robustness of DRAM operations by up to 12%. And this work is also open source, and you can check it from this slide. Now, the outline is this, but I'm going to skip motivation and background because of the time. So processing in memory is important, and DRAM is same. So maybe to refresh your minds, I'll just give you some brief background on in DRAM operations. For row copy, for example, row clone, here what we do is that, we copy source to, one source to one destination row in the prior works, which we call it row clone. So how this works is that you activate source, it asserts the source word line, it fetches source content to sense amplifiers, and you activate the destination, and then bit lines are still at source voltage, and then sense amplifiers still enabled. What happens is that source copy to destination. And how we do measure of 3 is that we just activate 3 rows at once at the same time, and the measured operation is performed. So for this example, we activate 3 rows simultaneously, which has A, B, and B, and which asserts 3 rows word lines and 3 rows perturbs bit lines simultaneously at the same time. And the sense amplifiers sample the output of majority. And our goal in this paper is the same as the prior previous paper, we want to experiment to understand the computational capability of off-the-shelf DRAM chips and analyze the robustness of such capability under various operating conditions. And for this one, we use DRAM Bender to test real DDR4 chips. But for this paper, we also include a power supply to actually change the voltage on the word line and to see how this affects the processing using DRAM operations, such as majority and row copy. And we test a total of 120 DDR4 chips from 2 major manufacturers. And we cover, again, different die divisions and chip densities, essentially DRAM architectures. So here, now we focus on a single subarray. And again, our comment sequence is the same, but row A and row B now are in the same subarray. And we carefully sweep these row addresses and the timing parameters in this comment sequence. And we sweep temperature from 50 degrees Celsius to 90 degrees Celsius. And we reduce the word line voltage from 2.5 volt to 2.1. And again, here to evaluate the robustness, we have success rate. It's the percentage of cells that produce the correct output, test into all test trials. And for example, for this example, the success rate is 66%. So now let's take a look at how we perform simultaneous many row activation. The key observation is that, again, the same activating 2 rows in quick succession can simultaneously activate many rows in a subarray. Here again, we have our subarray X. And when we, let's say, respect timing parameter, you know what happens. We just activate 1 row at a time. But if you violate it greatly, what happens is that we activate multiple rows. But now it's in the same subarray. So why this happens is that we have a hypothesis. It's because of the row decoder circuitry. So simultaneous many row activation is possible due to the hierarchical design of row decoder circuitry. We have the DRAM subarray, right? And in the DRAM subarray, we have a row decoder. What row decoder does is it just gets row address and decodes it and just asserts the corresponding word line. But to be able to do it very quickly, we have multiple stages of decoder so that we assert many signals in parallel, and hopefully one of them is correspond to that word line. And we just parallelly process row addresses for each decoder stage at the same time to make it fast, basically. So we can visualize this hierarchical row decoder circuitry as a tree. So each, let's say, level can be the stage, and each node can be the output of the decoder. And now let's see how we do it when we activate a single row. We activate row A. It decodes the row A address. It asserts the corresponding signals here, as you can see in the tree, multiple nodes, and follow the asserted nodes path from the root to leaf. You can think of that there are AND gates here from root to leaf, and if it's 1, then you assert the word line. And we wait for TRAS, and then we issue precharge, which will deassert every asserted signals in this tree. But what happens when we activate multiple rows? So back-to-back activate commands with violated timing asserts many more signals in the row decoder circuitry. So you know what happens when we issue activate row A, right? So when you issue back-to-back precharge and add to another row, it keeps the previously asserted signals because you interrupt precharge. And it decodes the row B addresses because you issue to activate row B and asserts corresponding signals. Since it follows the asserted nodes path, now you have multiple rows that is activated. Hopefully this is clear. And for more hypotheses and discussions, you can check the paper. And for this characterization, how we understand multiple rows is activated, we violate the timing and we issue write command. What happens is that write command overrides the activated row, right? So if we activate multiple rows, it should override that activated rows at the same time. Because in the write command, you don't give the row address, you just give the column address, because activate command does that. So if rows are activated, write command overrides all the activated rows content. So what we do is that we issue act per act for that subarray, and we issue write. After the write ends, we just precharge and read all the rows in that subarray to see which rows are activated. So for that, we carefully sweep row A and row B addresses and the timing parameters, And also we sweep temperature and word line voltages. And for this experiment, our key takeaways are off-the-shelf DRAM chips capable of simultaneously activating 2, 4, 8, 16, and 32 rows. And simultaneous many row activation is highly resilient to temperature and word line changes. So here, the success rate shows the percentage of cells overwritten with write commands. And the x-axis shows the number of simultaneously activated rows. As you can see, the average is almost 100% when you do this. So we conclude that off-the-shelf DRAM chips can simultaneously activate 2, 4, 8, 16, and 32 DRAM rows in the same subarray. So I'll just skip this. I have 5 minutes. So for majority operation, it's the same, right? So if you open 3 rows, you just have the majority of 3. If you open 5 rows, you just have the majority of 5, right? So, but we observe that we can activate 2, 4, 8, 16, and 32 rows, right? Not just numbers. So what do? We issue FRAC operation to make it VDD over 2, which is the same as the bit line voltage. So which makes it neutral during the multiple row activation. So to perform mesh 5 with 8 row activation, you put 3 rows into neutral rows so that 5 rows will perform this measured operation. Well, 3 rows doesn't affect anything. So to increase the robustness, what we do is that we store multiple copies. So you have 3 rows to perform measure to 3, right? So since we activate multiple rows, it reduces the, let's say, perturbation on the bit line, because some of them will need to try to pull down and some of them try to pull up the bit line voltage, right? But if we, let's say, multiply these copies, what happens is that it amplifies, right? Now it was, for example, 2x higher, 1x lower. Now 4x higher, 2x lower. So we amplify the difference, basically. Using that, we will have the correct result. So the characterization methodology is the same. We observe that off-the-shelf DRAM chips are capable of performing mesh 5, mesh 7, and mesh 9 operations. And storing multiple copies significantly increases the success rate. And voltage and temperature affect the success rate, whereas slightly affect, but whereas the data pattern affects significantly. So for this one, I'll just show very quickly. So as you can see, we can perform mesh 5, mesh 7, and mesh 9 operation. And when we replicate the inputs, we see that in some cases we have more than 50% of success rate increase on average. So storing multiple copies drastically increases the success rate of these measured operations. And the data pattern affects, to some extent, on average is 11%. And also temperature and word line voltage has a very small effect on this measured X operation. So for the multi-row copy, what we do is that we simultaneously activate multiple destination rows. Let's recall the row clone. We have source and destination, and we just, let's say, copy source through the sense amplifier, right? So in multi-row copy, what happens is that we know that we can activate multiple rows at the same time, right? So we activate the source first. Now it's in the sense amplifier, and now we violate the timings per charge and act, which will activate multiple rows, and which are hopefully our destinations. As a result, we will overwrite their content with the source. And hence, we call this multi-row copy operation. We observe that we can do that up to 31 other rows at very high success rate. And it's very resilient to data pattern, temperature, and voltage changes. And as you can see, it's the average is more than 99.98% for up to 31 destination rows, and data pattern at most affects less than 1%. And temperature and voltage has very small effect on these operations. Yes.
So for this operation, you do the first activate, like the source, then you wait nominal before doing pre, and then you do act pre with less than 3 nanosecond.
We observe that to be able to activate multiple rows, you just need to violate pre-charge to act, right? Because pre-charge will try to, let's say, deassert the word lines, but if you violate that, you will assert new signals. So as a result, you don't need to violate the timing for the first act. But if you do that, you will act. So this won't be simultaneous activation, right? Because the first row is already activated. So you cannot do it for majority. but it works here. Yes.
And the destination rows, it's not arbitrary, right? It's dependent on
It's depending on the row decoder circuitry.
So we don't have control over the destination. It's only one of the selected rows that the row decoder circuitry.
We reverse engineered that. There's a function actually. So if you select row A and row B, you will know which rows are going to open. So you can play with that because it's not transparent to the memory controller. So you don't know what's going on over there, which rows will be open. So you need to do an additional step of reverse engineering as we do.
So at first you profile,
yes.
And then you could know to which destination rows it's
yes.
written to.
Yes, which is not that much of a high overhead. There's one more question.
Does the pattern of neighboring cells play part in the success rate of the operation?
No. Here, for example, we say all zeros, all ones, and random, right?
Okay.
So the others are, let's say, the other rows are the complementary of this.
Okay.
So it doesn't have the.
So, for example, a replication of the majority operation wouldn't help in the success rate if we do the exact same for multiple columns. Would it help?
No, I don't think so. It depends on if it's not a perfect circuitry that you open some bits in the other rows, yeah, that will affect. But on the other hand, for these ones, at least the modules that I test doesn't affect that much.
Okay.
Okay, so I really need to conclude, I guess. Thank you. And there are a lot of details in the paper. So detailed hypothesis and key ideas, the hypothetical row decoder circuitry. Actually, there's a lower abstraction level of things over there. The hypothetical row decoder circuitry, how we activate things. The tree decoder isn't there. Input replication and more characterization results, especially the preliminary analysis of how power consumption will change when you activate multiple rows, and the effect of timing delays between activate precharge and precharge to activate comment, which maybe answer your question, an effect of temperature and word line, which I didn't add the plots here. And also we validate these results using SPICE experiment to gain more insight why input replication works. And potential performance benefits of enabling these operations. So you can find that in the paper, we have measured-based computations, and we show that enabling MASH5, MASH7 multi-row copy, which accelerates some kernels like addition, multiplication, some basic kernels. And also we have, I believe, an interesting use case as content destruction-based cold boot attack prevention. So basically over there is that you want to destroy your data as quick as possible. So you can use multi-row copy to do it very fastly. And I guess it's almost 20x. For those ones, please check the paper. And again, the discussions on the limitations we face. Version. Okay. Its paper is available on arXiv. And it's also open source and artifact evaluated. And you can check it out if you have the DRAM bundle at your home, you can test it. And let me conclude my talk for this lecture. The experiment demonstrated off-the-shelf DRAM chips can simultaneously activate up to 32 DRAM rows. We can perform MASH3, MASH5, MASH7, and MASH9 operations and copy one row's content up to 31 of the rows. And we characterize 120 DDR4 chips, and we observe that storing multiple copies will drastically increase the success rate of measured operations. And voltage and temperature slightly affect these measured operations, whereas data pattern affects significantly, and multi-row copy highly resilient to those changes. And again, we believe and hope that this will show the promising potential of using DRAM as a computation substrate. Thank you for your attention. If you have any questions, I'll have to answer. If not, thanks. Do we have questions? I guess no. Okay, thanks.